Picture yourself standing in your backyard on a clear night, gazing up at the countless stars scattered across the darkness above. Each point of light represents a sun, perhaps with its own family of worlds, each existing in its own pocket of space and time. What seems like a single moment to you, standing there on Earth, is experienced differently by every other observer in the cosmos. Time, as we will discover, is not the steady, universal heartbeat we once believed it to be. Time surrounds us like an invisible river, carrying us forward from one moment to the next. We measure it with clocks, mark it with calendars, and feel it in the rhythm of our days. Yet, what is time really? This question has puzzled humanity for millennia, from ancient philosophers contemplating the nature of existence to modern physicists peering into the deepest structures of reality. For most of human history, we understood time as absolute and universal. Imagine a great cosmic clock ticking away the seconds at the same rate everywhere in the universe. If it was noon on Earth, we believed it was noon throughout all of creation, from the nearest star to the most distant galaxy. This view seemed natural, even obvious. After all, when we look around us, time appears to flow at the same rate for everyone and everything. But this intuitive understanding, comfortable as it may be, is not how the universe actually works. Time is far stranger, far more malleable than our everyday experience suggests. It stretches and contracts, speeds up and slows down, depending on where you are and how fast you're moving through space. This revelation fundamentally changed our understanding of reality itself. To begin grasping this concept, we must first understand that time is not separate from the fabric of space. They are woven together into a single, unified entity that scientists call space-time. Picture a vast, flexible sheet stretched out in all directions. This sheet represents the very foundation of our reality, the stage upon which all cosmic events unfold. Every star, every planet, every particle of matter exists not just somewhere in space, but somewhere in time, occupying a unique coordinate in this four-dimensional tapestry. The revolutionary insight that led to this understanding came from a young patent clerk working in Bern, Switzerland at the beginning of the 20th century. His name was Albert Einstein, and his contemplations about the nature of light and motion would forever change how we see the universe. Einstein began with a simple yet profound observation. Light travels at the same speed for all observers, regardless of how fast they themselves are moving. This might seem like a minor technical detail, but its implications are staggering. If you're standing still and measure the speed of a passing beam of light, you'll get a certain value. If you're racing toward that same beam at tremendous speed, you might expect to measure a higher value, just as you would if you were running toward an approaching car. But that's not what happens. The speed of light remains exactly the same. This constancy of light speed forced Einstein to reconsider our basic assumptions about space and time. If light speed cannot change, then something else must give way. That something, Einstein realized, is time itself. As you move faster through space, time slows down for you relative to stationary observers. Move fast enough, and this effect becomes dramatic. Consider two identical twins. One remains on Earth while the other embarks on a journey through space at nearly the speed of light. From Earth's perspective, years pass normally. Seasons change, people age, technology advances. But aboard the speeding spacecraft, time passes much more slowly. The traveler ages only slightly while their earthbound twin grows old. When the spacefaring twin returns home, They might find their sibling has aged decades while they themselves have aged only months. This is not science fiction but established scientific fact. The effect is called time dilation, and it has been measured and confirmed countless times in laboratories and observations of the natural world. High-speed particles created in cosmic ray collisions live longer than they should based on their known lifespans, simply because they're moving so fast that time slows down for them. The mathematics of this phenomenon are elegant yet startling. As an object approaches the speed of light, time dilation becomes more and more extreme. At 90% the speed of light, time passes about twice as slowly. At 99%, it's 7 times slower. At 99.9%, it's more than 20 times slower. And at the speed of light itself, time would stop entirely, though no object with mass can actually reach this ultimate speed. This relationship between motion and time reveals something profound about the structure of reality. We live in a universe where space and time are not fixed, absolute quantities, but are relative to the observer. Your motion through space directly affects your journey through time. The faster you move through one dimension, the slower you move through the other. But motion is only part of the story. Einstein's insights led him to an even more remarkable discovery. Gravity itself affects the passage of time. This revelation emerged from what Einstein called his happiest thought, a moment of inspiration that came to him while contemplating a person falling freely from a building. In that moment of freefall, the person would feel weightless, as if gravity had simply vanished. This led Einstein to realize that gravity and acceleration are fundamentally the same phenomenon. Imagine you're in an elevator with no windows. If the elevator accelerates upward, you feel pressed against the floor, just as you do when standing on Earth's surface. If the elevator is in free fall, you float weightlessly, regardless of whether you're in a gravitational field or in the empty void of space. This equivalence between gravity and acceleration is the cornerstone of Einstein's general theory of relativity. The implications of this insight are breathtaking. If gravity is equivalent to acceleration, and if acceleration affects time, then gravity must also affect time. The stronger the gravitational field, the slower time passes. This means that time moves more slowly at Earth's surface than it does high above in orbit. The difference is tiny but measurable, and it has profound practical consequences for our modern world. Every day, we rely on a network of satellites orbiting high above our planet. These satellites form the Global Positioning System, or GPS, which helps us navigate from place to place with incredible precision. But for GPS to work accurately, it must account for the fact that time passes differently in orbit than it does on Earth's surface. The satellites orbit about 20,000 kilometers above Earth, where gravity is weaker than at the surface. Because of this weaker gravity, atomic clocks aboard the satellites run slightly faster than identical clocks on the ground. The difference is minuscule, just 38 millionths of a second per day. But in the world of GPS, this tiny discrepancy would accumulate into errors of several kilometers within a single day. To compensate, engineers program the satellite clocks to run slightly slower than they would naturally, so that when the effects of weaker gravity speed them up, they keep perfect time with Earth-based clocks. Without this correction based on Einstein's theories, GPS would be useless for precise navigation. Every time you use your phone to find directions, you're witnessing the practical application of time dilation. This gravitational effect on time becomes more dramatic in stronger gravitational fields. On the surface of the Sun, where gravity is 28 times stronger than on Earth, time passes measurably more slowly. On the surface of a white dwarf star, where gravity can be hundreds of thousands of times stronger than Earth's, the time dilation becomes substantial. And near the most extreme gravitational environments in the universe, the effects become almost unimaginable. Black holes represent the ultimate extreme of gravitational time dilation. These cosmic monsters are regions where matter has collapsed into such a dense point that their gravitational pull becomes infinitely strong at the center. Nothing, not even light itself, can escape from within a black hole's event horizon, the boundary beyond which escape becomes impossible. Near a black hole, the effects of gravitational time dilation become extraordinary. Imagine watching a friend fall toward a black hole while you remain safely far away. As your friend approaches the event horizon, you would see their movements becoming slower and slower. Their gestures would become languid, their speech would deepen and stretch out, and their image would redshift toward longer wavelengths of light. To you, watching from a distance, your friend would appear to freeze at the event horizon, their image fading and reddening until it disappeared entirely. But from your friend's perspective, nothing unusual would happen to their own experience of time. They would feel time passing normally as they crossed the event horizon and continued falling toward the center. The extreme time dilation would be invisible to them, just as the GPS satellite's slightly faster running clocks don't feel different to any hypothetical observers aboard them. This asymmetry reveals one of the most profound aspects of relativity. There is no universal, absolute perspective from which to view the universe. Every observer experiences their own version of events, their own flow of time, and all of these perspectives are equally valid. The universe doesn't have a master clock or a preferred reference frame. Instead, it's a symphony of relative experiences, each as real and meaningful as any other. The strongest gravitational time dilation we can observe occurs near stellar mass black holes scattered throughout our galaxy. But even more extreme effects happen near supermassive black holes, the giants that lurk at the centers of galaxies. These behemoths contain millions or billions of times the mass of our Sun, creating gravitational fields of incredible strength. At the center of our own Milky Way galaxy lies Sagittarius A star, a supermassive black hole containing about 4 million solar masses. Stars orbit this monster at tremendous speeds, some completing their orbits in just 16 years. As these stars swing close to the black hole during their elliptical orbits, they experience significant time dilation. From our perspective here on Earth, we can measure how their starlight is affected by both the intense gravity and their extreme orbital speeds. But let's journey even further into the cosmic abyss and consider what happens in the vicinity of the most massive black holes known to exist. Some supermassive black holes contain tens of billions of times the mass of our Sun. Near such monsters, space-time itself becomes so warped that the very concepts of space and time begin to lose their familiar meanings. Picture yourself approaching such a giant. As you fall inward, tidal forces would stretch your body, pulling more strongly on your feet than your head if you're falling feet first. But before these forces became uncomfortable, you would notice something far more strange. The universe behind you would appear to speed up dramatically. The stars would seem to evolve rapidly. Entire civilizations might rise and fall in what feels like moments to you. Meanwhile, any observers watching your descent would see you slowing down, your movements becoming more and more leisurely until you appeared to stop entirely at the event horizon. These extreme scenarios help us understand that time is not the simple, universal flow we experience in daily life. Instead, it's a dimension that can be stretched, compressed, and warped by the matter and energy in the universe. Every massive object creates its own unique distortion in space-time, its own modification of how time passes. But we don't need to venture near black holes to experience these effects. Even here on Earth, we live in a slightly warped space-time. Our planet's mass creates a gentle depression in the fabric of space and time, and this curvature affects everything on and around our world. The time dilation is incredibly small, but it's measurable with sensitive atomic clocks. If you were to carry an atomic clock up a mountain, you would find that it runs slightly faster at the higher altitude, where Earth's gravity is fractionally weaker. The effect is minuscule, just a few parts in a trillion, but it's real and detectable. This means that people living at high altitudes literally experience time passing slightly faster than those at sea level, though the difference is far too small to notice in everyday life. These insights transform our understanding of time from a river flowing at a constant rate to something more like a landscape with hills and valleys, fast currents and slow eddies. Every massive object creates its own temporal terrain, and every moving observer experiences their own unique journey through this landscape. The realization that time is relative and malleable raises profound questions about the nature of reality itself. If time can slow down and speed up, stretch and compress, what does this mean for our understanding of cause and effect, of memory and anticipation, of the very sequence of events that defines our existence? Consider the concept of simultaneity, the idea that events can happen at the same time. In our everyday experience, this seems straightforward. If two people clap their hands at exactly noon, we say these events are simultaneous. But relativity reveals that simultaneity is also relative. Events that appear simultaneous to one observer may not be simultaneous to another observer moving at a different speed or in a different gravitational field. Imagine two lightning strikes occurring on opposite sides of a moving train, perfectly synchronized from the perspective of someone standing on the platform. To that platform observer, the strikes are simultaneous. But to a passenger on the train, the lightning strike toward the front of the train appears to happen first, while the strike toward the rear happens slightly later. Both observers are correct from their own perspectives, but they disagree about the timing of events. This relativity of simultaneity means that the universe doesn't have a single universal now. Instead, every observer carries their own definition of the present moment, their own slice through the four-dimensional tapestry of space-time. The present is not a universal instant shared by all of creation, but a personal, subjective experience unique to each observer. This insight becomes even more profound when we consider observers separated by vast distances. The light from distant stars takes years to reach us, so when we look up at the night sky, we're seeing those stars not as they are now, but as they were when their light began its journey toward us. The star Betelgeuse, visible in the constellation Orion, is about 700 light-years away. The light entering your eyes left that star around the year 1300, when Earth was in the midst of the medieval period. But the question, what is happening in Betelgeuse right now, has no absolute answer. The now at Betelgeuse depends entirely on your reference frame. If you're at rest relative to both Earth and Betelgeuse, you might define now there as a specific moment 700 years in the future from when you see it. But if you're moving at high speed toward Betelgeuse, your definition of now there would be different. If you're moving away from it, your now would be different still. This relativity of simultaneity and the malleability of time lead us to a startling conclusion. The past, present, and future may all exist equally in a four-dimensional block universe. From this perspective, time doesn't flow from past to future. Instead, all moments exist simultaneously in the eternal structure of space-time. Our perception of time's passage might be more like a spotlight moving along a movie film, illuminating one frame at a time while all the frames exist equally on the reel. This view challenges our deepest intuitions about existence and identity. If all moments of your life exist equally in the block universe, what does it mean to say that you're aging or changing? Is the you of yesterday somehow less real than the you of today? Does the you of tomorrow already exist, waiting to be experienced? These questions venture into the realm of philosophy as much as physics, touching on fundamental issues of free will, consciousness, and the nature of existence itself. Some philosophers and physicists argue that if the block universe is real, then our sense of moving through time is an illusion created by our consciousness. Others maintain that the flow of time is genuine, even if it's more complex than we initially understood. The block universe perspective finds support in the mathematics of relativity, but it also raises troubling paradoxes. If all moments exist equally, what gives rise to our powerful sense that time flows? Why do we remember the past, but not the future? Why does causation seem to flow from earlier events to later ones if all times are equally real? These puzzles remain at the forefront of modern physics and philosophy of science. They remind us that despite our remarkable progress in understanding time's relationship to space and gravity, deep mysteries remain. The universe continues to surprise us with its subtlety and strangeness. As we contemplate these cosmic scales and relativistic effects, it's worth pausing to consider how time passes in different environments throughout our solar system. Each world in our cosmic neighborhood provides a unique laboratory for understanding time's behavior in varying gravitational fields and rotational conditions. On the Moon, where gravity is only 1/6 as strong as Earth's, atomic clocks would run slightly faster than they do on our planet's surface. The effect is small, but it would be measurable with sufficiently precise instruments. An astronaut spending a year on the Moon would age slightly more than their Earthbound twin, though the difference would be measured in nanoseconds. Mars, with its gravity about 38% of Earth's, would also experience slightly faster time passage than Earth. But Mars introduces another complication. Its day is about 24 hours and 37 minutes long, slightly longer than Earth's day. This difference in rotational period doesn't directly affect the rate of time passage, but it would certainly affect the, quote, biological rhythms of any human visitors, creating a complex interplay between cosmic time effects and biological time perception. Jupiter, the giant of our solar system, presents a more extreme case. With more than twice the gravity of Earth at its cloud tops, time would pass measurably more slowly there. But Jupiter is a gas giant without a solid surface, so the concept of standing on Jupiter is meaningless. Instead, we might consider the time dilation experienced by its many moons, each orbiting in Jupiter's powerful gravitational field. Io, the innermost large moon of Jupiter, experiences the strongest gravitational time dilation in the Jovian system. Racing around Jupiter every 42 hours in its close orbit, Io experiences both gravitational time dilation from Jupiter's strong field and kinematic time dilation from its rapid orbital motion. The combined effects would cause time to pass slightly more slowly on Io than on Earth, though again the differences would be minuscule. Europa, with its subsurface ocean possibly harboring life, experiences weaker gravitational effects due to its greater distance from Jupiter. But it still orbits within Jupiter's influence, creating its own unique temporal environment. Any hypothetical life forms in Europa's hidden ocean would experience time differently than life on Earth, though they would never notice the difference without an external reference. The outer planets present even more exotic temporal environments. Saturn, with its magnificent ring system, has a gravity similar to Earth's despite its much larger size, due to its lower density. But its numerous moons create a complex gravitational landscape with varying time dilation effects throughout the Saturnian system. Titan, Saturn's largest moon, has a dense atmosphere and surface lakes of liquid methane. Time passes there at nearly the same rate as on Earth, but the alien environment would make any human visitor acutely aware of being in a different world with different rhythms and cycles. The ice giants Uranus and Neptune, cold and distant, experience such weak solar radiation that their seasonal and daily cycles create temporal experiences utterly unlike anything on Earth. A year on Neptune lasts 165 Earth years, so a single Neptunian season spans more than 4 decades of Earth time. But to truly appreciate the cosmic diversity of temporal experience, we must venture beyond our solar system to consider how time passes on worlds orbiting other stars. Astronomers have discovered thousands of exoplanets, worlds that orbit stars other than our Sun, and each represents a unique temporal environment. Some exoplanets orbit so close to their host stars that they complete an orbit in just a few Earth days. On these worlds, years pass like weeks. Other planets orbit so far from their stars that a single year lasts thousands of Earth years. The diversity of orbital configurations creates an astounding variety of temporal rhythms throughout the galaxy. Consider a planet orbiting a red dwarf star, the most common type of star in the galaxy. Red dwarfs are much smaller and cooler than our Sun, so planets must orbit very close to receive enough warmth for liquid water. This close orbit means the planet would be tidally locked, with one side permanently facing the star and the other in eternal darkness. On such a world, the concepts of day and night would be replaced by permanent zones of light and darkness, creating a temporal experience unlike anything in our solar system. Planets orbiting binary star systems would experience even stranger temporal rhythms. Imagine a world with 2 suns, sometimes bathed in double daylight, sometimes experiencing partial eclipses as one star passes behind the other. The complex orbital mechanics would create intricate patterns of light and shadow, heat and cold, that would define the temporal experience of any inhabitants. Some exoplanets orbit extremely close to massive stars, experiencing gravitational time dilation effects much stronger than anything in our solar system. A planet orbiting close to a massive, dense star might experience time passing noticeably more slowly than on Earth. Conversely, a planet in a wide orbit around a low-mass star might experience time passing slightly faster than Earth time. The most extreme exoplanetary environments might exist around neutron stars, the incredibly dense remnants of massive stars that have exploded as supernovas. A neutron star contains more mass than our Sun compressed into a sphere just 20 kilometers across. The surface gravity is billions of times stronger than Earth's, creating extreme gravitational time dilation. While no planets have been confirmed orbiting neutron stars in habitable zones, their existence remains theoretically possible. Any world orbiting a neutron star would experience profound time dilation. Minutes on such a planet might correspond to hours or days of time experienced by distant observers. These cosmic comparisons help us appreciate the incredible diversity of temporal environments throughout the universe. Each world, each system, each region of space creates its own unique relationship with time. The universe is not just a collection of objects in space, but a vast symphony of different temporal experiences, each equally valid and real. This diversity extends beyond planets to the cosmic structures they inhabit. Galaxies themselves create large-scale gravitational fields that affect time's passage. The center of our Milky Way, dominated by its supermassive black hole, experiences stronger gravitational effects than the outer spiral arms where our solar system resides. Stars closer to the galactic center experience slightly stronger time dilation than we do in our outer suburb of the galaxy. The difference is incredibly small, but it's real. This means that civilizations near the galactic center, if they exist, would experience time passing slightly more slowly than we do. Galaxy clusters, the largest bound structures in the universe, create even larger scale gravitational effects. Our local group of galaxies, which includes the Milky Way, Andromeda, and several dozen smaller galaxies, sits within the gravitational influence of the much larger Virgo cluster. This vast collection of galaxies creates a weak but measurable gravitational field that affects time's passage throughout our cosmic neighborhood. The cosmic web itself, the largest structure in the universe, consists of filaments of dark matter and ordinary matter separated by vast empty voids. Regions within these filaments experience slightly stronger gravity than regions in the voids, creating a universe-spanning variation in the rate of time's passage. These cosmic variations in time's flow are incredibly subtle, far too small to affect biological processes or even the most sensitive atomic clocks we can currently build. But they represent a profound truth. There is no single, universal rate at which time passes. Every point in the universe experiences its own unique temporal environment, shaped by the distribution of matter and energy throughout the cosmos. This realization brings us to one of the most profound questions we can ask. Is time real, or is it merely an emergent property of more fundamental processes? Does time exist independently of the matter and energy that walk it, or does it arise from the interactions between particles and fields that make up reality? Different interpretations of physics suggest different answers to these questions. Some theories propose that time is indeed fundamental, woven into the basic structure of reality at the deepest level. Others suggest that time emerges from more basic processes, much like temperature emerges from the average motion of atoms without being a fundamental property of individual particles. The quantum mechanical description of reality adds another layer of mystery to our understanding of time. At the smallest scales, the distinction between past, present, and future becomes blurred. Quantum particles seem to exist in multiple states simultaneously until they're observed, and some interpretations suggest that quantum effects might influence the flow of time itself. The concept of quantum tunneling, where particles appear to traverse barriers faster than light should allow, raises questions about causation and temporal order at microscopic scales. Some experiments have even suggested that quantum effects might allow information to travel backward in time, though these interpretations remain highly controversial. The relationship between consciousness and time presents another deep puzzle. Our subjective experience of time's passage feels immediate and real, yet physics suggests that this experience might be an illusion created by our brain's processing of information. We remember the past and anticipate the future, creating a psychological arrow of time that might not correspond to any fundamental physical process. Neuroscience reveals that our brains construct our sense of time from multiple sensory inputs and internal rhythms. Brain damage can dramatically alter time perception, making minutes feel like hours, or causing patients to lose their sense of temporal sequence entirely. This suggests that our experience of time's flow is at least partly a construction of consciousness, rather than a direct perception of physical reality. Yet consciousness itself remains one of the greatest mysteries in science. We don't fully understand how subjective experience arises from objective physical processes, so we can't definitively say whether our sense of time's flow reflects something real about the universe or something particular about how conscious beings process information. These philosophical questions about time's reality have inspired countless works of science fiction and popular culture. Stories of time travel, temporal paradoxes, and alternate timelines capture our imagination precisely because they play with our deepest assumptions about the nature of reality. The 2014 film Interstellar brought many of these concepts to mainstream audiences, depicting astronauts experiencing extreme time dilation near a massive black hole. The movie's portrayal of time effects was based on real physics, consulting with theoretical physicists to ensure scientific accuracy. In the film, 1 hour on a planet near the black hole corresponds to 7 years on Earth, illustrating the dramatic effects of gravitational time dilation in extreme environments. The movie's emotional core centers on the human cost of these relativistic effects. A father watches video messages from his children as they grow up and age while he experiences only hours. This scenario, while fictional, illustrates a real consequence of Einstein's theories. Space travel at relativistic speeds or in strong gravitational fields would create profound temporal separations between travelers and those they leave behind. Other popular depictions of time often take more liberties with physics, imagining time machines that can transport people to the past or future at will. While such devices remain firmly in the realm of fiction, the scientific exploration of time's nature has revealed possibilities almost as strange as any science fiction story. Theoretical physicists have identified several scenarios that might allow for time travel, or at least time-like behavior. Rotating black holes, called Kerr black holes, create regions where the curvature of spacetime becomes so extreme that closed time-like curves become possible, paths through spacetime that loop back to their own past. Cosmic strings, hypothetical one-dimensional defects in spacetime left over from the early universe, might create similar effects if they exist and move at high speeds relative to each other. The resulting gravitational fields could theoretically allow for time travel, though the energy requirements and exotic matter needed make such scenarios purely speculative. Traversable wormholes, hypothetical tunnels through spacetime connecting distant regions, might also permit time travel if their two ends experience different gravitational environments. The accelerating expansion of the universe could naturally create the necessary time differences, though keeping such wormholes open would require exotic matter with negative energy density. These speculative possibilities remind us that our understanding of time and spacetime remains incomplete. While we have remarkably successful theories that describe how time behaves under a wide range of conditions, the deepest questions about time's nature remain open. The unification of general relativity with quantum mechanics might reveal new insights about time's fundamental character, or it might show that time itself is an emergent property of some deeper, more fundamental reality. The search for a theory of quantum gravity represents one of the greatest challenges in modern physics. String theory, loop quantum gravity, and other approaches each suggest different pictures of how space and time behave at the smallest scales. Some propose that space and time are made of discrete, indivisible units, like pixels in a cosmic computer screen. Others suggest that space and time emerge from more fundamental entities that don't themselves exist in space or time. These investigations push the boundaries of human knowledge and imagination. They force us to question our most basic assumptions about the nature of existence and our place within it. As we probe deeper into the mysteries of time and space-time, we discover that reality is far stranger and more wonderful than our everyday experience suggests. The practical implications of our growing understanding of time extend far beyond navigation satellites and exotic physics experiments. Precision timekeeping has become essential to modern technology, from computer networks to financial transactions to power grid synchronization. The global economy depends on synchronized clocks accurate to millionths of a second. Future technologies might exploit relativistic time effects in ways we're only beginning to imagine. Spacecraft using relativistic propulsion could allow astronauts to journey to distant stars and return to find centuries or millennia have passed on Earth. While this wouldn't violate causality or allow travel to the past, it would create a form of forward time travel, carrying passengers into Earth's future. Conversely, time dilation effects might be exploited to create temporal isolation, allowing important processes or computations to be carried out in environments where time passes more slowly. While the energy requirements would be enormous, future civilizations might use artificial gravitational fields or high-speed motion to create controlled temporal environments. The study of time's nature also influences our understanding of the universe's ultimate fate. The expansion of space affects how time passes between distant regions of the universe. As the expansion accelerates, driven by mysterious dark energy, regions of space become increasingly isolated from each other, each following its own temporal trajectory into an uncertain cosmic future. Current cosmological theories suggest that the universe will continue expanding and cooling for trillions of years, eventually reaching a state where stars stop forming and existing stars burn out. In this far future, time might become a meaningless concept as the universe approaches maximum entropy and minimal activity. Yet even this grim scenario remains uncertain, as our understanding of dark energy and the universe's fundamental properties continues to evolve. The multiverse hypothesis, suggesting that our observable universe is just one of countless bubble universes within a larger cosmic structure, raises additional questions about time's universality. If multiple universes exist with different physical laws and constants, each might experience time differently or might not experience time at all. Some versions of string theory suggest that the fundamental constants of nature, including those that determine how time behaves, might vary from one universe to another. In some universes, time might flow backward, or multiple time dimensions might exist, creating temporal experiences utterly unlike our own. These speculative scenarios remind us of how much we still don't know about time's true nature. Each discovery seems to raise new questions, revealing deeper layers of mystery in the structure of reality. The journey to understand time becomes a journey toward understanding existence itself. Yet for all the cosmic grandeur and theoretical complexity surrounding time's nature, we remain fundamentally temporal beings, experiencing reality one moment at a time. Our lives unfold in the rhythm of heartbeats and breath, in the cycle of sleeping and waking, in the progression from birth to death. We are embedded in time's flow, carried along by processes we can study, but cannot escape. This personal relationship with time gives urgency and poignancy to our scientific investigations. We study time not just as an abstract concept, but as the medium through which we experience everything we love and lose, everything we hope for and remember. Understanding time's nature helps us understand our own nature as beings who exist in time. The realization that time is relative and malleable might seem to diminish its importance, reducing our temporal experience to just one perspective among infinitely many. But perhaps the opposite is true. If every temporal experience is unique and valid, then our own experience of time becomes not less significant, but infinitely precious. Each moment of consciousness represents a unique perspective on the universe, a viewpoint that has never existed before and will never exist again. The particular way time passes for you, in your specific location and circumstances, is your own contribution to the cosmic symphony of temporal experiences that fills the universe. The stars continue their ancient dance overhead, each following its own path through space and time. Some are racing toward us, their light shifted toward bluer wavelengths by the Doppler effect. Others are receding, their light stretched toward red. All are participating in the general expansion of space itself, carrying them away from us at speeds proportional to their distance. Yet for all this cosmic motion and temporal complexity, the stars still inspire the same sense of wonder they brought to our ancestors. They still mark the passage of seasons and the rhythm of years. They still remind us of our place in a vast universe filled with mystery and beauty. Our understanding of time's relative nature doesn't diminish this wonder, but enhances it. We now know that each star exists in its own temporal environment, experiencing time in its own unique way. The massive blue giants age rapidly in their own reference frames, burning through their nuclear fuel in mere millions of years. The tiny red dwarfs age slowly, potentially shining for trillions of years, outlasting entire cosmological epochs. Binary star systems create cosmic laboratories for studying time's behavior in complex gravitational fields. As two stars orbit each other, they experience changing gravitational environments that cause their clocks to speed up and slow down in intricate patterns. If one star is much more massive than the other, it creates stronger time dilation effects, causing time to pass differently on each star despite their close proximity. When massive stars explode as supernovas, they create some of the most extreme temporal environments in the universe. The collapsing core forms a neutron star or black hole, regions where time dilation becomes extreme. Meanwhile, the expanding shockwave carries stellar material outward at significant fractions of the speed of light, creating relativistic time effects throughout the surrounding space. These stellar explosions also create and disperse the heavy elements necessary for planets and life. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all were forged in stellar cores and scattered by supernovas. We are literally made of star stuff, connected to the cosmic processes that shape time and space throughout the universe. This connection extends beyond mere chemistry to the very nature of our existence in time. The elements that make us possible were created billions of years ago in stellar cores, where time passed differently than it does on Earth today. The atoms in your body have experienced a vast range of temporal environments, from stellar interiors to interstellar space to the surface of a young planet where life began. In a sense, every atom carries with it a history of temporal experiences spanning cosmic time. The hydrogen atoms that make up much of your body formed in the first few minutes after the Big Bang, when the universe was unimaginably hot and dense, and time itself behaved differently than it does today. These primordial atoms have journeyed through 13.8 billion years of cosmic evolution, experiencing time's passage in countless different environments. The heavier elements in your body tell stories of stellar interiors, where nuclear fusion converted lighter elements into heavier ones over millions or billions of years. Each carbon atom in your DNA experienced time passing in the core of a massive star, where temperatures reached hundreds of millions of degrees and pressures crushed matter into exotic states. When those stars reached the end of their lives and exploded, the atoms that would eventually become part of you were hurled into space at tremendous speeds, experiencing relativistic time dilation as they raced through the galaxy. They may have spent millions of years drifting through the cold vacuum of interstellar space, where time passed at its natural rate, unmarked by the gravitational fields of nearby massive objects. Eventually, these wandering atoms found their way into the collapsing cloud of gas and dust that would become our solar system. During this collapse, they experienced changing gravitational fields as matter concentrated toward what would become the Sun. The atoms that ended up in Earth experienced different gravitational time dilation than those that became part of Jupiter or Mars. Once Earth formed and cooled, the atoms in your body began their most recent chapter of temporal experience. They may have spent billions of years cycling through rocks and oceans, atmosphere and living organisms, each environment providing its own subtle variations in the passage of time. Ocean depths experience slightly stronger gravity than mountain peaks, creating tiny differences in how time passes for atoms at different elevations. The biological processes that assembled these ancient atoms into living organisms introduced entirely new dimensions to their temporal experience. Life operates on multiple timescales simultaneously, from the rapid vibrations of molecular bonds to the slow rhythm of evolutionary change. Your heartbeat marks time on one scale, your breathing on another, your thoughts on yet another. The neurons in your brain fire electrical signals that travel at speeds much slower than light, creating tiny delays as information moves from one part of your brain to another. These delays are part of how your consciousness constructs its sense of temporal experience. The brain's processing creates the psychological arrow of time, the sense that moments flow from past through present toward future. Yet this neural processing happens within the framework of physical time as described by relativity. Your brain operates in Earth's gravitational field, experiencing the time dilation effects of our planet's mass. The electrical and chemical signals that create your thoughts are subject to the same relativistic effects as any other physical process. This intimate connection between consciousness and the physical nature of time creates profound questions about the relationship between mind and reality. Does consciousness merely observe the passage of time, or does it participate in creating our temporal experience? How does the subjective sense of duration relate to the objective measurement of time with clocks? Studies of altered states of consciousness provide intriguing clues about this relationship. Under the influence of certain substances or in specific meditative states, people report dramatic changes in their perception of time's passage. Minutes can feel like hours, or hours can pass in what seems like moments. These experiences suggest that consciousness plays an active role in constructing our sense of temporal flow. Brain injuries that affect time perception reveal the neural basis of our temporal experience. Damage to specific regions can cause patients to lose their ability to estimate durations accurately or to sequence events in proper temporal order. Some patients report feeling stuck in an eternal present, unable to connect current experiences with memories of the past or plans for the future. These medical insights remind us that our experience of time, however vivid and immediate it feels, is constructed by our brains from multiple sources of information. Like vision or hearing, temporal perception is an active process that creates our sense of reality from the raw data of sensory experience. The biological clocks that regulate our daily rhythms add another layer to our temporal experience. Circadian rhythms, driven by molecular oscillations within our cells, create an internal sense of time that roughly matches Earth's rotation period. These biological timepieces evolved to synchronize our physiology with the predictable cycle of day and night. But our circadian clocks are not perfectly accurate. Most people's internal rhythms run slightly longer than 24 hours, requiring daily adjustment by exposure to sunlight. This biological imprecision means that our internal sense of time's passage gradually drifts relative to clock time, creating subtle changes in how we experience duration and temporal sequence. Jet lag occurs when we travel rapidly across time zones, forcing our biological clocks out of synchronization with local solar time. The resulting discomfort reminds us that we are temporal beings, evolved to function within specific rhythmic patterns. Our biology expects time to pass in particular ways, with predictable alternations between light and dark, activity and rest. Space travelers face even more extreme challenges to their biological timekeeping. On the International Space Station, astronauts experience 16 sunrises and sunsets every 24 hours as they orbit Earth. This rapid cycling of light and dark can disrupt circadian rhythms, creating temporal disorientation that affects sleep, alertness, and cognitive function. Future space travelers journeying to Mars will face additional temporal challenges. A Martian day is about 37 minutes longer than an Earth day, and a Martian year lasts nearly twice as long as an Earth year. Human settlers on Mars would need to adapt their biological rhythms to these alien temporal cycles, while potentially maintaining communication schedules synchronized with Earth time. The challenge becomes even more complex when we consider interstellar travel. A journey to the nearest star would take thousands of years using current technology, or decades using hypothetical relativistic spacecraft. Time dilation effects would mean that travelers might age only months or years while Earthbound observers age decades or centuries. Such voyages would create unprecedented temporal separations between human populations. Travelers would return to find their homeworld changed beyond recognition, inhabited by people whose ancestors they knew before departure. The social and psychological implications of such temporal displacement remain largely unexplored. Yet these far-future scenarios help us appreciate the temporal environment we currently inhabit. Earth provides a stable gravitational field and rotational period that have remained essentially constant throughout human history. This temporal stability has allowed life to evolve complex rhythms and cycles that depend on predictable temporal patterns. The seasons mark longer temporal cycles that affect everything from plant growth to animal migration to human agriculture. These yearly rhythms emerge from Earth's tilted axis as our planet orbits the Sun, creating predictable variations in daylight and temperature that have shaped the evolution of life for billions of years. Even these fundamental temporal patterns have their subtle relativistic effects. Earth's orbit is slightly elliptical, so our planet moves faster when closer to the Sun and slower when farther away. This variation in orbital speed creates tiny changes in time dilation effects throughout the year, though the differences are far too small to measure without atomic clocks. The Moon's gravitational influence creates tidal cycles that mark time on yet another scale. Ocean tides rise and fall in complex patterns determined by the relative positions of Earth, Moon, and Sun. Many marine organisms have evolved biological clocks tuned to these tidal rhythms, creating internal senses of time that span roughly 12-hour periods. The Moon itself experiences time differently than Earth due to its weaker gravitational field. Clocks on the lunar surface would run slightly faster than identical clocks on Earth, accumulating a difference of about 38 microseconds per day. This tiny discrepancy would need to be accounted for in any future lunar colonies or scientific installations. As humanity expands beyond Earth, we will need to develop new approaches to timekeeping that account for relativistic effects across the solar system. A truly universal time standard might be impossible, but we could establish local standards for different regions of space while maintaining conversion protocols for communication between them. The challenges of space-based timekeeping pale in comparison to the temporal complexities we would face if we ever made contact with extraterrestrial intelligence. Any alien civilization would have evolved in its own unique temporal environment, shaped by the gravitational field and rotational period of its home world. Communication across interstellar distances would face fundamental temporal limitations imposed by the speed of light. A message sent to the nearest potentially habitable exoplanet would take more than 4 years to arrive, and any response would take another 4 years to return. This 8-year minimum delay would make real-time conversation impossible across interstellar distances. But the temporal challenges would extend beyond mere communication delays. If alien civilizations existed in significantly different gravitational fields, or traveled at relativistic speeds, they might experience time at very different rates than we do. A civilization near a massive star or black hole might experience days or years of subjective time while we experience centuries. These scenarios remind us that our own temporal experience, however central it feels to us, represents just one possibility among countless others throughout the universe. Every inhabited world would develop its own relationship with time, its own understanding of duration and sequence, its own biological and cultural rhythms. The diversity of temporal experience throughout the cosmos might be as vast as the diversity of planetary environments. Just as life has adapted to an incredible range of physical conditions, from deep ocean vents to frozen tundra to acidic hot springs, consciousness might adapt to an equally incredible range of temporal conditions. Some hypothetical civilizations might live much faster than we do, experiencing lifetimes in what we would consider minutes or hours. Others might live much slower, with thoughts and experiences unfolding over what we would consider geological timescales. Each would consider their own temporal rhythm natural, and might find ours alien and incomprehensible. These speculations help us appreciate the remarkable fact that we exist at all within the narrow range of temporal scales that support complex life. Our biological processes operate within a relatively small window of timescales, from the millisecond firing of neurons to the century-long span of human lifetimes. The universe operates on far vaster temporal scales. Stars form over millions of years and shine for billions. Galaxies rotate over hundreds of millions of years. The universe itself has been evolving for nearly 14 billion years and may continue changing for trillions more. Yet within this cosmic vastness, we find ourselves at what seems to be a special moment in cosmic history. We live during an era when stars are still forming and shining, when galaxies are still evolving and interacting, when the universe is neither too young nor too old to support complex structures and processes. This cosmic temporal context gives poignancy to our brief existence. We are temporary patterns of matter and energy, assembled for a brief time before dispersing back into the cosmic streams from which we came. Our consciousness represents a fleeting attempt by the universe to understand itself, to create meaning from the apparent randomness of physical processes. The realization that time is relative and that our temporal experience represents just one perspective among infinitely many might seem to diminish the significance of our lives. If time is not absolute, if our moments are not special, if our existence occupies only an infinitesimal slice of cosmic history, what meaning can our lives possess? Yet perhaps the answer lies in embracing rather than denying our temporal nature. We are not timeless beings observing time from outside. We are temporal beings embedded within time's flow. Our limitations define us as much as our capabilities. Our mortality gives urgency to our choices and poignancy to our experiences. The fact that time passes differently in other parts of the universe doesn't diminish the reality of how it passes for us. The fact that our temporal perspective is limited doesn't make it invalid. Each moment of consciousness represents a unique viewpoint on reality, a perspective that adds to the richness of the universe's self-awareness. In contemplating the nature of time, we join a conversation that spans cultures and centuries. Ancient philosophers wondered about time's passage and meaning. Medieval scholars debated whether time was created with the universe or existed independently. Enlightenment thinkers tried to understand time's relationship to space and motion. Each era has brought new insights and new questions. We now understand far more about time's physical nature than any previous generation, yet we face mysteries that our ancestors could never have imagined. The relationship between time and consciousness, the quantum nature of temporal processes, the origin and ultimate fate of time itself, all remain open questions. Our scientific instruments allow us to measure time with unprecedented precision, dividing seconds into billions of parts and detecting the tiny relativistic effects that permeate our daily lives. Yet this precision hasn't eliminated the mystery of time's nature, it has revealed new depths of complexity and wonder. The atomic clocks that define our modern time standards operate by measuring the vibrations of individual atoms, counting the oscillations of electromagnetic radiation absorbed or emitted by cesium or other elements. These measurements are so precise that the clocks can detect gravitational time dilation effects from moving just a few centimeters higher or lower in Earth's gravitational field. Such precision allows us to test Einstein's theories with extraordinary accuracy, confirming predictions that seemed impossibly abstract when first proposed. The agreement between theory and measurement stands as one of science's greatest triumphs, demonstrating that our mathematical descriptions of reality can capture truths about the universe's deepest structure. Yet even as we celebrate these successes, we remain aware of how much we don't know. Dark matter and dark energy, which together compose most of the universe, remain mysterious. The quantum nature of gravity eludes our understanding. The relationship between information and space-time puzzles physicists and philosophers alike. These uncertainties keep science vibrant and vital. Each answer reveals new questions. Each discovery opens new frontiers for exploration. The study of time continues to evolve, incorporating insights from quantum mechanics, cosmology, neuroscience, and philosophy. Future generations may develop theories of time that make our current understanding seem primitive or incomplete. They may discover that time has properties we haven't yet imagined, or that our concept of time itself needs fundamental revision. The history of science suggests that reality is always stranger and more wonderful than we expect. But whatever future discoveries await, the human experience of time will continue to shape our understanding of existence. We will always be temporal beings, experiencing reality one moment at a time, constructing meaning from the sequence of events that constitute our lives. The stars overhead continue their ancient journeys through space and time, each following paths determined by the fundamental forces of nature. Light from the most distant galaxies carries information about the universe's youth, when time itself was younger and the cosmic expansion was different than it is today. When we look deep into space, we look back in time, seeing the universe as it was billions of years ago. The cosmic microwave background radiation that fills all of space carries the afterglow of the Big Bang, showing us the universe when it was only 380,000 years old and transparent light could first travel freely through space. These ancient photons have been traveling through the expanding universe for more than 13 billion years, experiencing their own relativistic journey through cosmic time. From their perspective, traveling at the speed of light, no time has passed at all during their journey. They experience their emission and our detection as simultaneous events, despite the billions of years that separated them from our perspective. This cosmic perspective reminds us that time is not just a local phenomenon affecting our daily lives, but a fundamental aspect of reality that shapes the evolution of the entire universe. The Big Bang itself represents the beginning of time as we understand it, the moment when space-time itself came into existence along with matter and energy. Before the Big Bang, if "before" has any meaning in this context, time as we know it did not exist. The very concepts of causation, sequence, and duration that define our temporal experience emerged with the universe itself. Time and space, matter and energy all began together in the cosmic moment that set the stage for everything that followed. The early universe experienced time very differently than we do today. In the first moments after the Big Bang, when temperatures and densities were unimaginably extreme, the normal relationships between space, time, matter, and energy broke down. Quantum effects dominated over classical physics, and time itself may have had properties utterly unlike our current experience. As the universe expanded and cooled, the familiar structures of space-time gradually emerged. Particles condensed from pure energy, atoms formed from particles, stars ignited in the first clouds of hydrogen and helium. Each phase of cosmic evolution created new temporal environments, new ways for time to interact with matter and energy. The formation of the first black holes introduced regions of extreme time dilation into the universe. The birth of the first planets created new gravitational environments where time passed at slightly different rates. The emergence of life added biological time to the cosmic inventory of temporal experiences. Now, billions of years later, we find ourselves in a universe rich with temporal diversity. Every star, planet, and galaxy creates its own unique relationship with time. Consciousness has emerged to experience and contemplate this temporal landscape, adding subjective time to the objective measurements of physics. We are temporal beings in a temporal universe, products of processes that unfold across cosmic timescales. Our consciousness represents time's attempt to understand itself, matter's effort to comprehend the temporal framework within which it exists. As we stand beneath the night sky, contemplating the nature of time and our place within it, we participate in one of the universe's most remarkable achievements. Arrangements of atoms that were forged in stellar cores have organized themselves into brains capable of pondering the deepest questions about existence. Time has given rise to beings that can study time itself. The journey through these concepts, from the everyday ticking of clocks to the cosmic expansion of space-time, reveals the extraordinary nature of the reality we inhabit. Time is neither the simple, absolute flow we intuitively expect, nor a mere illusion created by consciousness. Instead, it emerges as something far more subtle and beautiful, a fundamental dimension of existence that interweaves with space, matter, and energy to create the rich tapestry of physical reality. Our exploration has taken us from GPS satellites correcting for relativistic effects to black holes where time nearly stops, from the brief lifetimes of quantum particles to the billion-year cycles of SESI. Galactic rotation. We have seen how motion affects time's passage, how gravity warps temporal flow, and how the expansion of space creates new relationships between cosmic time and cosmic distance. We have contemplated the possibility that all moments exist simultaneously in a four-dimensional block universe, challenged our assumptions about the flow of time, and wondered whether consciousness plays a fundamental role in creating temporal experience. We have imagined civilizations experiencing time at radically different rates and considered how space travel might separate us temporally from our fellow humans. Through it all, we have discovered that time is both more complex and more beautiful than we initially imagined. It connects us to the stars through shared relativistic effects, to the ancient universe through the cosmic background radiation, and to future generations through the ongoing expansion of space itself. Yet for all this cosmic grandeur, time remains intimately personal. It is the medium through which we experience love and loss, hope and memory, the quiet satisfaction of understanding, and the excitement of discovery. Our temporal nature doesn't diminish our significance, it defines our humanity. We are travelers in a vast cosmic ocean, riding currents of space-time that carry us from past toward future. The journey is brief by cosmic standards, but infinite in its possibilities for meaning and discovery. Each moment offers new opportunities to experience wonder, to create beauty, to understand truth, and to connect with the magnificent reality that surrounds us. The stars that inspired our ancestors continue to inspire us, but now we understand them as fellow travelers in space-time, each following its own temporal trajectory through the expanding universe. We see them not as distant lights, but as cosmic neighbors, sharing the same fundamental physical laws that govern time's passage throughout all of creation. In learning about time's relative nature, we discover our own place in the cosmic story. We are neither outside observers looking in, nor insignificant specks in an uncaring void. We are integral parts of the universe's ongoing evolution, temporary arrangements of matter and energy that have achieved the remarkable ability to understand the temporal framework within which we exist. This understanding brings both humility and wonder. Humility, because we recognize our brief span in cosmic time and our limited perspective on cosmic processes. Wonder, because we realize that despite these limitations, we have achieved genuine insight into time's nature and our relationship to the cosmos. As our journey through these ideas draws to a close, we might pause to appreciate the extraordinary fact that time has allowed us to understand time. Through billions of years of cosmic evolution, matter has organized itself into forms capable of comprehending the very principles that govern its existence. Consciousness has emerged as time's way of knowing itself. We began by standing in a backyard, looking up at stars that seemed fixed and eternal. We end with a deeper appreciation of those same stars as dynamic, evolving systems embedded in the flowing fabric of space-time. The view has changed not because the stars are different, but because our understanding has grown. Time continues its mysterious flow, carrying us forward into an uncertain but wonder-filled future. Each moment brings new possibilities for discovery, new opportunities to deepen our understanding of the cosmos and our place within it. We remain temporal beings in a temporal universe, but now we understand something of what that means. The cosmic ocean stretches endlessly around us, its currents shaped by the distribution of matter and energy throughout space and time. We navigate these currents not as passive passengers, but as conscious explorers, using our brief journey to map the waters and understand the forces that move us. In doing so, we participate in the universe's greatest adventure, its ongoing effort to understand itself through the consciousness it has created. The stars overhead continue their ancient dance, but now we hear the music that guides their steps. It is the rhythm of space-time itself, the cosmic symphony of which we are both audience and performers. Our understanding of time's nature allows us to appreciate our role in this grand composition, temporary notes in an eternal song that spans the cosmos. In the end, time remains as mysterious as it is familiar, as profound as it is personal. We may never fully comprehend its ultimate nature, but our journey toward understanding enriches both our knowledge and our wonder. We are time's children, born from its flow and destined to return to it, but blessed with the remarkable gift of consciousness that allows us to contemplate the miracle of our own temporal existence. The universe continues its expansion, space continues its growth, and time continues its eternal passage. We continue our journey as well, carried forward by forces we can study but cannot escape, participants in a cosmic story whose ending remains unwritten. In our brief moment of consciousness, we have glimpsed something of time's true nature and our place within its flow. That glimpse illuminates not just the cosmos, but ourselves. Yet our exploration of time's mysteries has only begun to scratch the surface of this profound subject. As we delve deeper into the nature of temporal reality, we discover layers upon layers of complexity that challenge our understanding and stretch our imagination. The universe reveals itself as an intricate clockwork of interconnected processes, each operating on its own temporal scale, while contributing to the grand symphony of cosmic evolution. Consider the vast hierarchy of timescales that operates throughout the natural world. At the smallest scale, quantum particles exist and interact in time frames measured in fractions of seconds so small they defy ordinary comprehension. A photon of light oscillates trillions of times per second, its electromagnetic field cycling through peaks and valleys faster than any mechanical process could follow. These quantum rhythms form the fundamental timekeeper of atomic processes, determining how electrons orbit nuclei and how chemical bonds form and break. Moving up in scale, we encounter the realm of molecular motion, where complex organic molecules dance their intricate choreography of life. Proteins fold and unfold in milliseconds. Enzymes catalyze reactions in microseconds. And DNA replicates itself with clockwork precision over periods of hours. These biological timescales bridge the gap between the quantum world and the macroscopic realm of living organisms. The human body operates as a symphony of biological clocks, each tissue and organ maintaining its own rhythmic patterns while coordinating with the others. Heart cells beat in synchrony, creating the familiar lub-dub rhythm that marks our passage through life. Brain waves oscillate at different frequencies, from the rapid gamma waves associated with focused attention to the slow delta waves of deep unconsciousness. Hormonal cycles unfold over days and weeks, regulating everything from growth to reproduction to immune function. These biological rhythms evolved within Earth's gravitational field and rotational period, fine-tuned over billions of years to optimize survival and reproduction within our planet's specific temporal environment. The circadian clock that regulates our daily cycles is synchronized to Earth's 24-hour rotation, but it's flexible enough to adjust to seasonal changes in daylight duration and strong enough to brash maintain rhythm even in constant darkness. Yet these same biological processes would behave differently in other gravitational environments. An astronaut's heart would beat at the same rate on the Moon as on Earth, but time itself would pass slightly faster in the Moon's weaker gravitational field. Over the course of a lunar mission lasting several months, an astronaut's biological clocks would gradually drift relative to Earth time, creating subtle but measurable differences in aging and cellular processes. The implications become more dramatic when we consider longer space missions or permanent settlement of other worlds. Humans living on Mars would adapt their biological rhythms to the slightly longer Martian day, but they would also experience the subtle effects of Mars's weaker gravity on the passage of time itself. Over generations, these small differences might accumulate into measurable changes in human physiology and lifespan. Future space colonies might need to maintain artificial gravity systems not just for physical health, but for temporal consistency with Earth. Rotating habitats could provide artificial gravity equal to Earth's, ensuring that time passes at the same rate for colonists as it does for their relatives back home. Without such measures, the gradual temporal drift between populations could create practical challenges for communication, trade, and family relationships. The challenge of maintaining temporal coherence across a spacefaring civilization represents one of the most subtle but significant obstacles to human expansion beyond Earth. Each world, each habitat, each spacecraft would exist in its own slightly different temporal environment. The accumulated effects of these differences could eventually fragment humanity into temporally isolated populations, each aging at different rates and experiencing history on different timescales. These considerations lead us to contemplate the deeper question of whether time truly flows or whether our perception of temporal passage is an artifact of consciousness operating within a static four-dimensional space-time. The block universe interpretation suggests that all moments of time exist simultaneously, like frames in an infinitely long movie reel. From this perspective, the past hasn't ceased to exist, and the future hasn't yet come into being. Instead, all times are equally real and eternal. This view finds support in the mathematics of relativity, where space-time is treated as a unified four-dimensional structure. Events don't happen in time and space, they simply exist at specific coordinates in space-time. Your birth, your present moment of reading these words, and your eventual death are all equally real points in the four-dimensional manifold of space-time, connected by your world line through the cosmic fabric. Yet this mathematical description conflicts with our immediate experience of temporal flow. We feel time passing, remember the past but not the future, and sense ourselves moving from one moment to the next. This experiential reality seems to demand an explanation that goes beyond the static block universe model. One possibility is that consciousness itself creates the illusion of temporal flow through the process of information integration. Your brain constantly assembles sensory data into coherent perceptions, and this assembly process might create the sensation of moving through time. Each moment of consciousness represents a snapshot of neural activity, and the sequence of these snapshots creates the narrative thread of subjective experience. The arrow of time that we experience so vividly might emerge from the second law of thermodynamics, which dictates that entropy tends to increase over time. This fundamental principle creates a preferred direction in time, distinguishing past from future, even in a universe where the basic physical laws are time-symmetric. We remember the past because our brains are complex systems that naturally preserve information about lower entropy states, while we cannot remember the future because it represents higher entropy states that have not yet crystallized into definite form. This thermodynamic arrow of time connects our personal temporal experience to the broader cosmic processes that shape the universe's evolution. The expansion of space, the formation and evolution of stars, the chemical enrichment of galaxies, all represent irreversible processes that give time its directional character. We are not separate from these cosmic processes, but intimately connected to them through the physical laws that govern both our consciousness and the universe at large. The quantum mechanical description of reality adds another layer of complexity to our understanding of time's nature. At the microscopic scale, particles seem to exist in multiple states simultaneously until they are observed or measured. This quantum superposition appears to violate our classical understanding of temporal sequence, suggesting that cause and effect relationships might be more subtle than we typically assume. Quantum entanglement creates correlations between particles that persist regardless of the distance separating them. When two particles are entangled, measuring one instantly affects the state of the other, even if they are separated by vast distances. This spooky action at a distance, as Einstein called it, seems to violate the principle that nothing can travel faster than light, yet it has been confirmed by countless experiments. The implications of quantum entanglement for our understanding of time remain hotly debated among physicists and philosophers. Some interpretations suggest that entangled particles share a kind of temporal connection that transcends ordinary spacetime, while others maintain that entanglement doesn't actually involve faster-than-light communication. These debates touch on fundamental questions about the nature of reality and the role of observation in determining physical outcomes. Quantum field theory, the most successful framework for describing particle physics, treats time as a parameter rather than a dynamical quantity. In this formulation, particles are excitations in underlying quantum fields that permeate all of spacetime. The creation and annihilation of particles represents changes in these fields over time, but time itself is treated as a fixed background against which these changes occur. Yet even this sophisticated framework struggles with the problem of quantum gravity, the challenge of describing how space-time itself behaves according to quantum mechanical principles. At the smallest scales, where quantum effects become comparable to gravitational effects, our current theories break down and new physics must emerge. String theory, one of the leading candidates for a theory of quantum gravity, suggests that the fundamental constituents of reality are not point particles, but tiny vibrating strings. These strings exist in a higher dimensional spacetime, with the extra dimensions curled up so tightly that they remain invisible at ordinary scales. In this framework, time might have properties that we haven't yet discovered, possibly including multiple time dimensions or discrete rather than continuous structure. Loop quantum gravity takes a different approach, suggesting that spacetime itself has a granular structure at the smallest scales. According to this theory, space and time are not infinitely divisible but consist of discrete units, like pixels in a cosmic computer screen. This quantization of spacetime might resolve some of the paradoxes that arise when quantum mechanics and general relativity are combined. These speculative theories remind us that our current understanding of time, however sophisticated, remains incomplete. The deepest questions about time's nature await future discoveries that might revolutionize our understanding of reality itself. We stand at the frontier of knowledge, peering into mysteries that challenge our most basic assumptions about existence. The practical implications of these theoretical advances could be profound. If time truly has a quantum structure, future technologies might exploit this structure to create new forms of computation or communication. If multiple time dimensions exist, we might discover ways to access them, opening possibilities that currently exist only in science fiction. The study of time also intersects with our understanding of consciousness and free will. If the block universe interpretation is correct and all moments exist simultaneously, what does this mean for our sense of choice and agency? Are our decisions genuine choices that shape the future, or are they simply events that exist eternally in the four-dimensional structure of space-time? Different philosophical traditions offer different answers to these questions. Some argue that free will is incompatible with a deterministic block universe, while others maintain that our choices can be real and meaningful even if they exist eternally in space-time. The debate touches on fundamental questions about the nature of consciousness, causation, and moral responsibility. Neuroscience adds another perspective to these discussions by revealing the neural basis of decision-making and temporal perception. Brain imaging studies show that unconscious neural activity often begins several hundred milliseconds before people report being aware of their intention to act. This finding has been interpreted as evidence against free will, though others argue that it simply reveals the complex, multi-layered nature of conscious decision-making. The relationship between brain activity and subjective experience remains one of the deepest mysteries in science. We don't understand how objective physical processes in neurons give rise to subjective, qualitative experiences like the sensation of temporal flow. This hard problem of consciousness intersects with questions about time's nature in ways that we're only beginning to explore. Some theories suggest that consciousness might play a fundamental role in the physical universe, possibly even participating in the collapse of quantum wave functions or the creation of temporal experience. These ideas remain highly speculative, but they remind us that consciousness and time might be more intimately connected than we currently understand. The evolution of consciousness itself represents one of the most remarkable chapters in the cosmic story of time. Over billions of years, matter organized itself into increasingly complex forms, eventually giving rise to nervous systems capable of processing information about temporal relationships. The development of memory allowed organisms to learn from past experiences and plan for future events, creating new forms of temporal awareness. Human consciousness represents the current pinnacle of this evolutionary process, at least on Earth. We possess an unprecedented ability to think about time abstractly, to imagine past and future scenarios, and to understand the mathematical principles that govern temporal relationships. This cognitive capacity allows us to transcend our immediate temporal environment and contemplate the nature of time itself. Language plays a crucial role in our temporal cognition, providing the conceptual tools we need to think and communicate about time. Different languages structure temporal concepts in different ways, influencing how their speakers think about duration, sequence, and temporal relationships. Some languages have complex tense systems that encode precise information about when events occurred relative to the moment of speaking, while others use simpler temporal markers that leave many temporal relationships implicit. The metaphors we use to think about time also shape our understanding. In English, we often conceptualize time as flowing like a river or moving like a conveyor belt, with ourselves as stationary observers watching events pass by. Other cultures use different metaphors, sometimes imagining themselves moving through time or visualizing temporal relationships in spatial terms that differ from our own. These linguistic and cultural differences remind us that our particular way of experiencing and conceptualizing time is not universal or inevitable. Human consciousness has developed various approaches to understanding temporal reality, each offering its own insights and limitations. The scientific study of time represents just one of many possible ways of engaging with temporal experience, though it has proven remarkably successful at revealing time's objective properties. Art and literature have long explored the subjective dimensions of temporal experience, capturing aspects of time's nature that pure scientific description might miss. Poetry can convey the emotional weight of temporal passage, the poignancy of memory, and the anxiety of anticipation in ways that complement scientific understanding. Music unfolds in time, creating structures of rhythm and melody that mirror the temporal patterns of consciousness itself. The great works of literature often center on characters' relationships with time, exploring themes of memory, aging, mortality, and the search for meaning within temporal limitations. These artistic explorations remind us that time is not just a scientific concept, but a lived reality that shapes every aspect of human experience. Religious and spiritual traditions have also grappled with time's nature, often developing concepts that transcend ordinary temporal experience. Ideas of eternity, reincarnation, and timeless spiritual realms represent attempts to understand human existence within a larger temporal context. These traditions remind us that questions about time's ultimate nature touch on the deepest concerns of human existence. The integration of scientific, philosophical, artistic, and spiritual perspectives on time creates a rich, multifaceted understanding that no single approach could achieve alone. Each perspective illuminates different aspects of temporal reality, contributing to a comprehensive picture that honors both time's objective properties and its subjective significance. As we look toward the future, new technologies promise to deepen our understanding of time while raising new questions about its nature. Quantum computers might allow us to explore temporal paradoxes and information processing in ways that classical computers cannot. Advanced space missions will test relativistic effects over longer periods and greater distances than ever before. The search for extraterrestrial intelligence might reveal other forms of consciousness that experience time in radically different ways. Contact with alien civilizations could challenge our assumptions about temporal experience and reveal new possibilities for understanding time's nature. The diversity of temporal experience across the cosmos might prove as vast as the diversity of planetary environments and biological forms. Future developments in neuroscience and artificial intelligence might shed new light on the relationship between consciousness and temporal experience. As we develop more sophisticated models of neural information processing, we might better understand how brains create the sense of temporal flow and whether this sense could be reproduced in artificial systems. The possibility of creating artificial consciousness raises profound questions about the nature of temporal experience. Would an artificial intelligence experience time the way humans do, or would it develop entirely different forms of temporal awareness? Could we design AI systems that experience multiple streams of temporal consciousness simultaneously, or that process information in ways that transcend ordinary temporal limitations? These speculative possibilities remind us that our exploration of time's nature is far from complete. Each discovery reveals new horizons for investigation, new questions that push the boundaries of our understanding. The study of time remains one of the most active and challenging areas of scientific and philosophical inquiry. The practical applications of our growing understanding of time continue to expand. Precision timekeeping enables technologies from global positioning systems to financial trading networks to power grid synchronization. Future applications might include gravitational wave detectors that can measure space-time distortions with unprecedented precision, quantum communication networks that exploit temporal correlations between entangled particles, and navigation systems for interstellar spacecraft that must account for complex relativistic effects. The economic implications of temporal research are already substantial and likely to grow. The global economy depends increasingly on synchronized timing across vast networks of computers and communication systems. High-frequency trading relies on nanosecond precision timing to execute financial transactions. The Internet itself requires precise time coordination to route data packets efficiently across global networks. Future economic systems might exploit relativistic time effects in ways we're only beginning to imagine. Space-based manufacturing might use controlled gravitational fields to create precisely timed chemical reactions. Interplanetary commerce might need to account for time dilation effects when calculating compound interest or contract fulfillment deadlines. The social and cultural implications of our expanding temporal understanding are equally profound. As human civilization spreads beyond Earth, we'll need to develop new social institutions that can function across multiple temporal reference frames. Legal systems might need to define concepts like contract duration and criminal responsibility in ways that account for relativistic effects. Educational systems will need to help students understand increasingly complex temporal concepts as these ideas become more relevant to daily life. The mathematics of space-time and the principles of relativity might become as essential to general education as basic arithmetic and literacy. The psychological implications of living in a relativistic universe are only beginning to be explored. How might widespread understanding of time's relative nature affect human culture and social relationships? Will knowledge that time passes differently in various environments change how we think about aging, mortality, and the meaning of life? Some philosophers argue that understanding time's relative nature might lead to greater acceptance of diversity and different perspectives. If there's no single absolute temporal reference frame, perhaps there's no single absolute perspective on truth or value. Others worry that relativistic thinking might lead to nihilism or the abandonment of shared standards for knowledge and ethics. These debates reflect deeper tensions between scientific understanding and human meaning-making. The challenge lies in integrating our growing knowledge of time's objective properties with our need for subjective significance and shared values. Science reveals what the universe is like. Wisdom helps us understand what that means for how we should live. The environmental implications of temporal research also deserve consideration. Our growing ability to measure and manipulate time might enable new approaches to environmental monitoring and climate science. Precise timing measurements could help us track environmental changes with unprecedented accuracy, while understanding gravitational effects might reveal new ways to monitor ocean currents, atmospheric chi, dynamics, and geological processes. Climate change itself represents a temporal challenge that operates on scales much longer than human political and economic cycles. Understanding time's nature might help us develop better frameworks for thinking about long-term environmental stewardship and intergenerational responsibility. The medical applications of temporal research are already beginning to emerge. Chronobiology, the study of biological rhythms, is revealing how temporal disruption contributes to various diseases and how timing can optimize therapeutic interventions. The development of increasingly precise medical timing protocols might lead to more effective treatments with fewer side effects. Future medical technologies might exploit quantum timing effects for diagnostic purposes or use controlled gravitational fields to influence biological processes. The intersection of temporal physics and biology represents a frontier of research with enormous potential for improving human health and understanding life's fundamental processes. The ethical implications of temporal manipulation deserve careful consideration. If we develop technologies that can significantly alter the passage of time, how should they be used? Should time dilation technologies be available to everyone, or might they create new forms of inequality between those who can afford to slow their aging and those who cannot? The possibility of temporal manipulation raises questions about fairness, justice, and the distribution of life's fundamental resources. If some people can experience more subjective time than others by exploiting relativistic effects, does this create ethical obligations to ensure equal access to temporal experiences? These ethical challenges parallel those we face with other powerful technologies, from genetic engineering to artificial intelligence. The key lies in developing frameworks for responsible innovation that maximize benefits while minimizing risks and ensuring equitable access to new capabilities. The relationship between temporal research and fundamental questions about existence continues to evolve. As we learn more about time's nature, we gain new perspectives on classic philosophical problems about identity, consciousness, causation, and the meaning of life. If the block universe interpretation is correct, and all moments exist simultaneously, what implications does this have for how we think about death and legacy? If past and future are equally real, perhaps death doesn't represent the absolute end of existence, but simply a boundary in our particular temporal trajectory through space-time. These speculative possibilities offer both comfort and challenge. They might provide new ways of thinking about loss and grief, but they also force us to reconsider basic assumptions about existence and identity. The integration of scientific and philosophical perspectives on time remains an ongoing project that touches the deepest aspects of human experience. The role of mathematics in understanding time deserves special attention. The language of mathematics has proven remarkably effective at describing temporal relationships, from the simple equations of motion to the complex tensor equations of general relativity. This mathematical description of time raises profound questions about the relationship between abstract mathematical structures and physical reality. Some physicists and philosophers argue that mathematics doesn't just describe reality but constitutes it, but the universe is essentially mathematical in nature. From this perspective, time's mathematical properties aren't approximations of some deeper reality, but are the reality itself. The elegant mathematical relationships that govern temporal phenomena might represent the universe's fundamental operating principles. Others maintain that mathematics is a human invention that happens to be useful for describing natural phenomena but doesn't capture the full richness of temporal experience. The subjective sense of time's passage, the emotional weight of memory, and the existential significance of mortality might require non-mathematical approaches to understanding. The tension between mathematical and experiential approaches to time reflects broader questions about the relationship between objective and subjective reality. Science excels at revealing time's objective properties, but human experience encompasses dimensions that might not be fully captured by mathematical description. The future of temporal research likely lies in integrating multiple approaches to understanding time's nature. Mathematical physics will continue to reveal new aspects of space-time structure, while neuroscience illuminates the biological basis of temporal experience. Philosophy helps us think clearly about conceptual problems, while art and literature explore the existential dimensions of temporal existence. This integrative approach recognizes that time is both a physical phenomenon subject to scientific investigation and a lived reality that shapes human consciousness and culture. Understanding time fully requires engaging with both its objective properties and its subjective significance. The cosmic perspective on time reminds us that our temporal experience, however central it feels to us, represents just one thread in the vast tapestry of cosmic evolution. We are temporal beings in a temporal universe, products of processes that have been unfolding for billions of years and will continue for billions more. Yet this cosmic perspective need not diminish our sense of significance. Instead, it might enhance our appreciation for the remarkable fact that the universe has given rise to beings capable of understanding time's nature. We are not separate from the cosmic processes we study, but integral parts of them, arrangements of matter and energy that have achieved the extraordinary capacity for self-reflection and understanding. The journey toward understanding time's ultimate nature continues, carried forward by countless researchers, thinkers, and dreamers who share humanity's ancient fascination with temporal mysteries. Each generation builds upon the insights of previous generations while pushing into new territories of knowledge and understanding. As we continue this collective exploration, we might remember that understanding time is ultimately about understanding ourselves and our place in the cosmos. We are temporal beings seeking to comprehend the temporal framework within which we exist. This quest for understanding reflects something fundamental about consciousness itself, the drive to make sense of existence and find meaning within the flow of time. The universe has spent billions of years creating conditions suitable for complex structures and processes, including the emergence of consciousness capable of contemplating its own nature. In studying time, we participate in the universe's ongoing project of self-understanding, contributing our own small part to the vast cosmic conversation about the nature of existence. This cosmic conversation echoes across vast scales of space and time, from the quantum fluctuations that govern particle interactions to the large-scale structure of the universe itself. Each level of reality contributes its own voice to the symphony of temporal experience, creating harmonies and dissonances that reflect the deep interconnectedness of all physical processes. At the quantum level, particles exist in a strange temporal twilight, where past, present, and future seem to blur together. Virtual particles pop into existence and vanish again in timeframes so brief that they violate the normal relationship between energy and time, borrowing energy from the vacuum itself for infinitesimally short periods. These quantum fluctuations create a kind of temporal foam at the smallest scales, where the smooth fabric of spacetime gives way to a chaotic dance of creation and annihilation. The uncertainty principle, one of quantum mechanics' most fundamental insights, reveals that we cannot simultaneously know both the exact position and momentum of a particle with perfect precision. This limitation isn't merely a consequence of measurement difficulties, but reflects something fundamental about the nature of reality itself. The universe seems to be built on a foundation of uncertainty that extends to temporal relationships as well. Quantum tunneling allows particles to traverse energy barriers that should be impossible to cross according to classical physics. In these processes, particles seem to travel faster than light for brief intervals, raising profound questions about causality and the relationship between quantum mechanics and relativity. The resolution of these apparent paradoxes continues to challenge physicists, and they require new frameworks for understanding the relationship between space, time, and information. The phenomenon of quantum entanglement creates correlations between particles that persist across arbitrary distances, seemingly instantaneously. When two particles become entangled, measuring one immediately affects the quantum state of the other, regardless of the spatial separation between them. This spooky action at a distance appears to violate the principle that nothing can travel faster than light, yet experiments have confirmed its reality with extraordinary precision. The implications of quantum entanglement for our understanding of time remain hotly debated. Some interpretations suggest that entangled particles share a kind of temporal connection that transcends ordinary spacetime, while others maintain that no information actually travels between them faster than Chamana. White. Light. These debates touch on fundamental questions about the nature of information, causality, and the structure of reality itself. Recent experiments have pushed the boundaries of quantum temporal effects even further. Scientists have demonstrated quantum superposition of temporal order, where events can exist in a superposition of happening in different sequences simultaneously. In these strange quantum scenarios, event A can be both before and after event B, until a measurement collapses the temporal superposition into a definite sequence. These quantum temporal effects suggest that time's nature at the microscopic scale might be far stranger than our macroscopic experience suggests. The classical notion of a well-defined temporal sequence might be an emergent property that only appears when quantum systems become large enough to behave classically. At the quantum level, time itself might be subject to the same uncertainty and superposition that characterize other quantum properties. The intersection of quantum mechanics and gravity remains one of the greatest unsolved problems in physics. The two theories describe reality using fundamentally different mathematical frameworks that resist unification. Quantum mechanics treats spacetime as a fixed background against which particles and fields evolve, while general relativity treats spacetime itself as a dynamic entity that curves and warps in response to grainy matter and energy. Various approaches to quantum gravity suggest different pictures of how time might behave at the smallest scales. In some theories, time becomes quantized, existing in discrete chunks rather than flowing continuously. Others propose that time emerges from more fundamental processes that don't themselves exist in time, much like temperature emerges from the average motion of atoms without being a property of individual particles. The concept of emergent time has profound implications for our understanding of causality and temporal order. If time emerges from timeless processes, then the flow of time we experience might be more like the appearance of wetness in water, a collective property that arises from the interactions of countless underlying components that don't themselves possess this property. String theory, one of the leading candidates for a quantum theory of gravity, suggests that the fundamental constituents of reality are not point particles, but tiny vibrating strings. These strings exist in a higher dimensional spacetime, with the extra dimensions curled up so tightly that they remain invisible at ordinary scales. In this framework, time might have properties that we haven't yet discovered, possibly including multiple temporal dimensions or connections to the hidden spatial dimensions. The mathematics of string theory are extraordinarily complex, requiring sophisticated techniques from abstract algebra and geometry. The theory predicts the existence of objects called branes, higher dimensional surfaces on which strings can end. Our entire observable universe might be confined to one such brane, floating in a higher dimensional space that contains multiple time dimensions and exotic forms of matter and energy. If string theory is correct, the apparent flow of time in our universe might be just one manifestation of more complex temporal relationships that operate in the full higher dimensional space. Events that seem causally disconnected in our three-dimensional space might be intimately connected through paths that wind through the extra dimensions, creating possibilities for temporal relationships that transcend our current understanding. Loop quantum gravity takes a different approach to the problem of quantum spacetime, suggesting that space and time themselves have a granular structure at the smallest scales. According to this theory, spacetime is not infinitely divisible, but consists of discrete units, like pixels in a cosmic computer screen. These quantum grains of spacetime are incredibly small, many orders of magnitude smaller than the smallest particles we can currently detect. If spacetime truly has this granular structure, then time itself might tick forward in discrete jumps, rather than flowing continuously. The smooth passage of time that we experience would be like the apparent motion in a movie, created by the rapid succession of static frames that change so quickly that they create the illusion of continuous motion. This quantization of time would have profound implications for our understanding of temporal processes. Physical events would unfold not continuously but in discrete steps, with each step corresponding to the fundamental time interval determined by the quantum structure of spacetime itself. The implications for causality, consciousness, and the nature of temporal experience remain largely unexplored. The search for a successful theory of quantum gravity continues to drive some of the most advanced research in theoretical physics. New approaches regularly emerge, each offering its own perspective on how space, time, matter, and information might be related at the deepest level. These investigations push the boundaries of human knowledge and imagination, forcing us to consider possibilities that stretch far beyond our ordinary experience. The relationship between information and spacetime has emerged as a central theme in modern physics. Information theory, originally developed to understand communication and computation, now provides crucial insights into the nature of black holes, the structure of spacetime, and the relationship between quantum mechanics, and gravity. Black holes present a fundamental puzzle known as the information paradox. According to general relativity, anything that falls into a black hole is lost forever, crushed to infinite density at the central singularity. But quantum mechanics suggests that information cannot be destroyed, only transformed. This apparent contradiction has led to decades of research into the quantum nature of black holes and the fate of information that crosses the event horizon. Recent work suggests that black holes might not destroy information, but instead encode it on their surfaces in a holographic manner. The event horizon itself might function like a cosmic hard drive, storing information about everything that has ever fallen into the black hole. When black holes eventually evaporate through Hawking radiation, this information might be gradually released back into the universe, preserving the quantum mechanical principle of information conservation. This holographic principle has far-reaching implications for our understanding of spacetime and reality itself. It suggests that the three-dimensional volume of space might be fundamentally described by information encoded on its two-dimensional boundary, much like a hologram encodes three-dimensional images on a flat surface. From this perspective, the interior of any region of space might be redundant information that can be reconstructed from data stored on the boundary. If the holographic principle is correct, then the nature of time and temporal experience might be fundamentally different from what we imagine. The flow of time might be an emergent property that arises from the processing of information encoded on cosmic boundaries, rather than a fundamental aspect of reality itself. Our subjective experience of temporal passage might be like watching a movie projected from a holographic storage medium, where the sensation of motion through time emerges from the sequential processing of static information. The study of complex systems has revealed another perspective on time's nature through the concept of emergent phenomena. Complex systems can exhibit behaviors and properties that are not present in their individual components, much like consciousness emerges from neural networks, or life emerges from chemical reactions. Time itself might be an emergent property that arises from the collective behavior of more fundamental processes. Emergent time could explain why time seems to flow at the macroscopic scale while appearing more fluid and uncertain at the quantum level. Just as the solid properties of a rock emerge from the electromagnetic interactions between atoms that are themselves mostly empty space, the consistent flow of time might emerge from quantum processes that don't themselves respect our classical notions of temporal order. This emergence perspective suggests that understanding time's ultimate nature might require studying how temporal properties arise from the collective behavior of quantum systems. The transition from quantum to classical behavior, known as decoherence, might play a crucial role in creating the stable temporal relationships that characterize our macroscopic experience. The role of observation and measurement in quantum mechanics adds another layer to our understanding of time's relationship to consciousness. The Copenhagen interpretation of quantum mechanics suggests that quantum systems exist in superposition until they are observed, at which point the wave function collapses into a definite state. This measurement process seems to require the involvement of conscious observers, suggesting a fundamental connection between consciousness and the structure of reality. If consciousness plays a role in collapsing quantum wave functions, then it might also play a role in determining the nature of temporal relationships. The subjective experience of time's flow might not be merely a byproduct of neural processing, but an active participant in the creation of temporal reality. This possibility remains highly speculative, but has attracted serious consideration from some physicists and philosophers. The many worlds interpretation of quantum mechanics offers a different perspective on time and consciousness. According to this view, every quantum measurement causes the universe to split into multiple parallel branches, each corresponding to a different possible outcome. Consciousness experiences only one branch, but all branches are equally real and continue evolving according to the laws of physics. In the many worlds framework, time becomes a branching structure rather than a single linear progression. Every moment presents multiple possible futures, and the universe explores all of them simultaneously. Our experience of a single timeline is just one path through this vast branching structure of parallel realities. This interpretation has profound implications for our understanding of choice, causality, and personal identity. If every possible decision creates a parallel universe where you make a different choice, then all possible versions of your life are equally real. The you that exists now is just one branch of a cosmic tree that contains infinite variations of your existence. The philosophical implications of these quantum mechanical interpretations continue to be debated among physicists and philosophers. They challenge our basic assumptions about the nature of reality, causality, and the role of consciousness in determining physical outcomes. These debates remind us that our understanding of time's relationship to quantum mechanics remains incomplete and may require fundamental revisions to our current theories. The thermodynamic arrow of time provides another crucial perspective on why time appears to flow in a particular direction. The second law of thermodynamics states that entropy, a measure of disorder, tends to increase over time in isolated systems. This principle creates a preferred direction in time, distinguishing past from future even in a universe where the fundamental physical laws are time-symmetric. The increase of entropy over time manifests in countless ways throughout the natural world. Hot objects cool down, organized systems become disorganized, and energy flows from concentrated to dispersed forms. This universal tendency toward increasing disorder creates the arrow of time that we experience so vividly in our daily lives. Yet the relationship between thermodynamic time and subjective time remains mysterious. Why does the increase of entropy correspond so closely to our psychological sense of temporal direction? Is this correspondence merely a consequence of our brains being thermodynamic systems that naturally align with the universe's entropic flow, or does it reveal something deeper about the relationship between Bia, consciousness, and physical law? Some theories suggest that consciousness itself might be fundamentally related to the processing of information and the creation of order from disorder. Living systems, including conscious beings, are remarkably effective at creating local pockets of decreased entropy, organizing matter and energy into complex functional structures. This ability to create order might be intimately connected to our experience of temporal flow and our sense of agency in shaping the future. The relationship between life, consciousness, and time becomes even more intriguing when we consider the possibility of life existing in very different physical environments. Extremophile organisms on Earth have shown that life can adapt to conditions previously thought impossible, from the intense heat of volcanic vents to the crushing pressures of deep ocean trenches to the high radiation environments near nuclear reactors. These discoveries suggest that life might be possible in environments with very different temporal characteristics than those we experience on Earth's surface. Organisms living near massive gravitational sources might experience significant time dilation, living their entire life cycles in what we would consider slow motion. Conversely, life forms in weak gravitational fields might experience accelerated time relative to Earth-based life. The implications for biological evolution in such environments are fascinating to contemplate. Natural selection operates through differential reproduction over multiple generations, but the temporal scale of this process would be dramatically different in altered gravitational environments. Evolution near a massive star might proceed much more slowly from our perspective, while evolution in space habitats with artificial gravity might proceed at accelerated rates. These considerations become relevant as we contemplate the possibility of spreading life beyond Earth. Future space colonies might need to consider not just the physical challenges of different environments, but also the temporal implications of living in altered gravitational fields. The gradual accumulation of temporal differences could eventually lead to biological and evolutionary divergence between populations living in different gravitational environments. The search for extraterrestrial life takes on new dimensions when we consider the diversity of possible temporal environments throughout the universe. Life might exist on worlds with very different day-night cycles, seasonal patterns, and gravitational time dilation effects. Each form of life would have evolved its own relationship with time, its own biological rhythms and temporal adaptations. Contact with extraterrestrial intelligence would face not just the challenge of communication across vast distances, but also the challenge of coordinating across different temporal reference frames. A civilization living near a massive gravitational source might experience years of subjective time, while we experience centuries. Establishing meaningful communication protocols would require careful consideration of these relativistic effects. The possibility of machine intelligence adds another layer to these considerations. Artificial intelligences might experience time very differently than biological organisms, potentially processing information at rates far faster or slower than biological neural networks. The subjective experience of an AI might unfold on timescales radically different from human consciousness. Future AI systems might be designed to operate across multiple temporal scales simultaneously, processing real-time sensory information while also considering long-term trends and patterns that unfold over years or decades. Such systems might develop forms of temporal awareness that transcend the limitations of biological consciousness, potentially offering new insights into the nature of time and temporal experience. The relationship between computation and time presents its own set of fascinating questions. Digital computers process information in discrete steps, with each computational operation taking a finite amount of time. The speed of computation is ultimately limited by the time required for signals to travel between different parts of the computer and for transistors to switch between different states. Quantum computers promise to transcend some of these limitations by exploiting quantum mechanical properties like superposition and entanglement. Quantum algorithms can, in principle, explore multiple computational paths simultaneously, potentially solving certain problems exponentially faster than classical computers. This quantum speedup might be understood as a form of temporal parallelism, where quantum systems explore multiple timelines of computation simultaneously. The implications of quantum computing for our understanding of time and information processing continue to unfold as these technologies develop. Quantum computers might eventually allow us to simulate complex temporal phenomena that are beyond the reach of classical computation, providing new insights into the relationship between time, information, and physical reality. The development of increasingly sophisticated timing technologies has practical implications that extend far beyond scientific research. Modern financial markets rely on nanosecond precision timing to execute high-frequency trades, with even tiny timing advantages translating into significant economic gains. The global positioning system requires atomic clock precision to provide accurate navigation data, while Internet protocols depend on synchronized timing to route data efficiently across global networks. Future technologies will likely place even greater demands on precision timing. Quantum communication networks will require exquisite synchronization to maintain quantum entanglement across large distances. Autonomous vehicles will need precise timing coordination to navigate safely in complex environments. Smart grids will require temporally coordinated energy distribution to optimize efficiency and reliability. The economic value of precise timing continues to grow as our technological systems become more complex and interconnected. The ability to measure and control time with ever greater precision has become a fundamental enabling technology for modern civilization, comparable in importance to electricity or telecommunications. The social implications of our expanding temporal capabilities deserve careful consideration. As we develop technologies that can manipulate the passage of time through relativistic effects, we may need to address questions of temporal equity and justice. Should time dilation technologies be available to everyone, or might they create new forms of inequality between those who can afford to alter their temporal experience and those who cannot? The possibility of using time dilation for life extension raises particularly complex ethical questions. If some people can slow their aging by exploiting gravitational time dilation or high-speed travel, this could create unprecedented disparities in lifespan and life experience. The social fabric might be strained by growing gaps between those who age normally and those who remain young through temporal manipulation. Legal systems would face unprecedented challenges in defining concepts like contract duration, property rights, and criminal liability in a world where different people experience time at different rates. If two people sign a 10-year contract but one experiences significant time dilation during that period, how should the contract terms be interpreted? These questions will require careful thought as temporal technologies become more sophisticated. Educational systems will need to help people understand increasingly complex temporal concepts as these ideas become more relevant to daily life. Basic literacy in space-time physics may become as essential as traditional literacy and numeracy. Students will need to understand not just how to read and calculate, but how to think about time, causality, and relativistic effects. The challenge of temporal education extends beyond technical knowledge to include the philosophical and existential implications of our expanding understanding of time's nature. How do we help people integrate scientific knowledge about time's relativity with their personal need for meaning and temporal orientation? How do we preserve human values and social cohesion in a universe where time itself proves to be more complex and strange than we ever imagined? Cultural adaptation to relativistic realities may prove as challenging as technological adaptation. Human cultures have evolved sophisticated mechanisms for coordinating social activities across time, from shared calendars and schedules to cultural narratives about past and future. These mechanisms may need fundamental revision as we become a truly spacefaring species living across multiple temporal reference frames. The preservation of cultural continuity across temporal separations presents unique challenges. How do we maintain shared traditions and values when different populations experience time at different rates? How do we preserve historical memory and cultural identity when space travel creates temporal gaps between generations? These questions become particularly poignant when we consider the possibility of interstellar colonization. Colonists traveling to distant stars would experience time dilation effects that could separate them temporally from Earth by decades or centuries. They would arrive at their destination to find that Earth has aged far more than they have, potentially changing beyond recognition during their journey. The psychological implications of such temporal separation remain largely unexplored. How would it feel to return from an interstellar journey to find that everyone you knew had died of old age while you remained young? How would society adapt to the presence of temporal refugees from the past? People who had been away so long that their cultural knowledge and social connections had become obsolete. These scenarios may seem like distant science fiction, but they illustrate the profound human implications of temporal physics. As our technological capabilities expand, we will need to develop new frameworks for thinking about identity, relationships, and social organization in a relativistic universe. The intersection of temporal physics and environmental science offers another area of growing importance. Climate change operates on temporal scales that span decades to centuries, requiring long-term thinking that challenges traditional political and economic frameworks. Understanding time's nature might help us develop better approaches to environmental stewardship and intergenerational responsibility. Precision timing technologies are already contributing to environmental monitoring and climate research. Atomic clocks can detect tiny changes in Earth's gravitational field caused by melting ice sheets and changing ocean currents. GPS timing systems enable precise tracking of atmospheric changes and geological processes. These applications demonstrate how temporal technology can contribute to understanding and addressing environmental challenges. Future environmental applications might exploit relativistic effects for enhanced monitoring capabilities. Satellites in different gravitational environments experience time at slightly different rates, and these differences might be exploited to create new forms of environmental sensors. The gravitational signature of environmental changes might be detectable through careful measurement of time dilation effects. The medical applications of temporal research continue to expand as we better understand the biological basis of timing and rhythm. Chronobiology has revealed that virtually every aspect of human physiology follows circadian rhythms, from hormone production to immune function to cognitive performance. Disruption of these rhythms contributes to a wide range of health problems. from sleep disorders to metabolic diseases to mental health conditions. Future medical treatments might exploit our growing understanding of biological timing to optimize therapeutic interventions. Drug delivery systems could be designed to release medications at precisely the right times to maximize effectiveness and minimize side effects. Surgical procedures might be timed to coincide with optimal biological rhythms for healing and recovery. The possibility of using controlled time dilation for medical purposes remains speculative but intriguing. Could patients with certain conditions benefit from experiencing time at different rates? Might controlled gravitational fields be used to slow aging or accelerate healing processes? These applications would require extraordinary technological capabilities, but they illustrate the potential medical implications of advanced temporal manipulation. The study of aging itself takes on new dimensions when viewed through the lens of relativistic physics. Biological aging is fundamentally a temporal process involving the accumulation of molecular damage over time. Understanding how time dilation affects biological processes might provide new insights into aging mechanisms and potential interventions. Space medicine already confronts some of these questions as astronauts experience extended periods in altered gravitational environments. Long-duration spaceflight affects human physiology in complex ways, some of which might be related to the subtle time dilation effects experienced in orbit. As space missions become longer and travel to more distant destinations, these effects will become more pronounced. The psychological aspects of temporal experience in extreme environments deserve special attention. Astronauts on long-duration missions report changes in their perception of time and temporal relationships. The artificial environment of spacecraft, with controlled lighting and atmospheric conditions, can disrupt normal circadian rhythms and create temporal disorientation. Future space travelers journeying to other star systems would face even more extreme temporal challenges. The isolation from Earth's temporal rhythms, combined with significant time dilation effects, could create unprecedented psychological stresses. Maintaining mental health and social cohesion during such journeys will require careful attention to temporal factors. The development of virtual reality technologies offers new possibilities for managing temporal experience in extreme environments. Virtual environments could provide temporal cues and rhythms that help maintain psychological well-being during long space journeys. These technologies might also allow people to experience different temporal environments virtually, providing preparation for actual space travel or simply expanding human understanding of temporal diversity. The relationship between time and creativity presents another fascinating area of investigation. Artists, writers, and musicians have long recognized that creative work often involves altered relationships with time. The experience of creative flow can involve losing track of time entirely, with hours passing unnoticed as attention becomes completely absorbed in creative activity. Neuroscience research is beginning to reveal the brain mechanisms underlying these altered temporal states. Creative activities seem to involve changes in the brain's default mode network, the collection of brain regions that are active during rest and introspection. These changes might affect how the brain processes temporal information, creating the subjective experience of time distortion during creative work. Understanding the neurobiology of temporal experience during creative states might lead to new approaches for enhancing creativity and artistic expression. Brain stimulation techniques that affect temporal processing might be able to induce creative states more reliably. Virtual reality environments that manipulate temporal perception might provide new platforms for creative exploration. The preservation and transmission of creative works across different temporal environments presents unique challenges. How do we preserve artistic and cultural expressions in ways that remain meaningful across different temporal reference frames? How do we ensure that the temporal aspects of artistic works, like musical rhythm and poetic meter, translate appropriately across different time dilation environments? These questions become particularly relevant as we consider the long-term future of human civilization. Cultural preservation across cosmic timescales requires thinking about how to maintain meaning and relevance across temporal separations that dwarf anything in human history. The challenge is not just technical but fundamentally about what aspects of human experience we consider most important to preserve. The philosophical implications of our expanding understanding of time continue to evolve as new discoveries challenge traditional concepts. The relationship between time and free will remains one of the most contentious areas of debate. If the block universe interpretation is correct and all moments exist simultaneously, what does this mean for our sense of choice and moral responsibility? Different philosophical traditions offer various approaches to these questions. Compatibilists argue that free will is compatible with determinism and the block universe, while hard determinists maintain that genuine free will is impossible if the future already exists. Hard incompatibilists argue that free will is incompatible with both determinism and indeterminism, while libertarians maintain that genuine free will requires an open future. These debates are not merely academic but have practical implications for how we think about moral responsibility, legal accountability, and personal agency. If our actions are already determined by the structure of the block universe, how do we justify punishment for criminal behavior or praise for heroic actions? These questions challenge fundamental assumptions about justice, ethics, and human nature. The emerging field of temporal ethics attempts to address these challenges by developing frameworks for moral reasoning that take seriously the relativistic nature of time. These approaches consider how moral obligations and responsibilities might change when different agents experience time at different rates, or when actions have consequences that unfold across different temporal reference frames. The question of temporal justice becomes particularly complex in scenarios involving time travel or extreme time dilation. If someone commits a crime and then travels to the future through time dilation, how should the legal system respond? If actions in the past can affect the future through causal loops, how do we assign responsibility for outcomes that seem to violate normal temporal causation? These scenarios may seem purely hypothetical, but they help clarify our underlying assumptions about the relationship between time, causation, and moral responsibility. As our technological capabilities expand, we may need to address such questions in practical rather than merely theoretical terms. The relationship between time and personal identity presents another area of philosophical challenge. If the block universe is real and all moments of your life exist simultaneously, what defines your identity across time? Are you the same person as your past and future selves, or are these different individuals connected by causal relationships but not identical in any meaningful sense? The problem of personal identity through time has ancient roots but takes on new dimensions in light of modern physics. If consciousness is somehow fundamental to the collapse of quantum wave functions, then the role of conscious observation in determining physical reality might extend to the construction of personal identity itself. These questions become particularly acute when considering the possibility of uploading consciousness to digital substrates, or creating multiple copies of the same individual. If identity is tied to continuity of consciousness, How do we define identity when consciousness can be copied, backed up, or distributed across multiple physical substrates? The temporal aspects of consciousness uploading present unique challenges. If consciousness is uploaded to a computer system that processes information much faster than biological brains, the uploaded individual might experience subjective time at a dramatically accelerated rate. Conversely, if the computer system is slower than biological cognition, the uploaded consciousness might experience time in slow motion relative to biological humans. These scenarios raise profound questions about the nature of conscious experience and its relationship to time. Would an uploaded consciousness that experiences accelerated time still be the same person as the original biological individual? How do we maintain meaningful relationships across such temporal separations? The possibility of consciousness existing in quantum computers or other exotic substrates adds additional complexity to these questions. Quantum information processing might enable forms of consciousness that exist in superposition states or that experience multiple temporal timelines simultaneously. Such possibilities stretch our concepts of identity and experience beyond their current limits. The study of time consciousness in altered states provides another window into the relationship between subjective experience and temporal reality. Psychedelic experiences often involve dramatic alterations in time perception, with users reporting experiences of eternal moments, backwards time flow, or the simultaneous experience of multiple temporal perspectives. These altered states might provide clues about the brain mechanisms that normally create our sense of temporal flow and continuity. By studying how psychedelic substances affect temporal perception, researchers might gain insights into the neural basis of time consciousness and its relationship to other aspects of conscious experience. Meditation and contemplative practices also offer insights into the nature of temporal experience. Advanced meditators report achieving states of consciousness where the normal sense of temporal flow disappears, replaced by a sense of eternal presence or timeless awareness. These experiences suggest that our ordinary temporal consciousness might be just one possible mode of experiencing reality. The implications of these findings for our understanding of time's ultimate nature remain unclear. Do altered states of consciousness reveal aspects of temporal reality that are normally hidden, or do they simply demonstrate the brain's capacity to construct different types of temporal experience? The answer might have profound implications for our understanding of both consciousness and time. The integration of scientific, philosophical, and experiential approaches to understanding time continues to reveal new depths of complexity and beauty in temporal reality. Each perspective contributes unique insights that no single approach could achieve alone. The scientific method reveals time's objective properties. Philosophical analysis clarifies conceptual relationships, and direct experience provides the subjective foundation that gives time its triple existential significance. This integration suggests that understanding time's ultimate nature might require embracing multiple ways of knowing, rather than reducing everything to a single explanatory framework. The richness of temporal reality might only be fully appreciated through the combined insights of physics, philosophy, neuroscience, psychology, and contemplative traditions. The future of temporal research likely lies in developing new forms of interdisciplinary collaboration that can bridge these different approaches to understanding time. Such collaboration might lead to breakthrough insights that transform our understanding of time, consciousness, and reality itself. As we continue this collective exploration, we might remember that the study of time is ultimately inseparable from the study of existence itself. Time provides the framework within which all change, all process, all experience unfolds. Understanding time more deeply means understanding the very fabric of reality in which we find ourselves embedded. We are temporal beings in a temporal universe, products of cosmic evolution that has been unfolding for billions of years. Our consciousness represents time's achievement of self-awareness, matter's capacity to reflect upon the temporal processes that brought it into being. In studying time, we participate in the universe's ongoing project of understanding itself. This participation carries with it a profound responsibility. As conscious beings capable of understanding time's nature, we become stewards of temporal knowledge and guardians of the cosmic conversation about existence itself. Our discoveries about time are not merely academic achievements but contributions to the universe's growing self-awareness, threads in the vast tapestry of understanding that spans from quantum mechanics, cosmology. The responsibility extends beyond knowledge to action. Understanding time's relative nature changes how we might choose to live our lives and organize our societies. If time is not absolute but depends on our motion through space and our position in gravitational fields, then every choice about where to go and how fast to travel becomes a choice about how to experience time itself. This temporal agency represents a new form of freedom that previous generations could never have imagined. We are approaching an era where conscious beings might deliberately choose their temporal experience, selecting rates of aging and subjective time flow through technological manipulation of relativistic effects. Such capabilities would transform the human condition in ways that we are only beginning to contemplate. The emergence of temporal choice raises profound questions about what we value most in existence. Do we want to experience time at its natural rate, accepting the traditional rhythms of aging and mortality? Or do we want to slow our temporal experience, stretching our lives across longer periods of cosmic time? Different choices would lead to radically different forms of human experience and social organization. Some might choose to live faster, experiencing more subjective time within shorter periods of cosmic time. Such individuals might pack lifetimes of experience into what others would consider brief intervals, living intensely accelerated lives that burn brightly but briefly against the cosmic background. Others might choose the opposite path, slowing their temporal experience to witness cosmic processes that unfold over geological or astronomical timescales. These choices would inevitably create new forms of temporal diversity within human populations. We might see the emergence of temporal subspecies, groups of humans who have adapted to very different rates of temporal experience. Fast-time humans might develop enhanced cognitive abilities and accelerated cultural evolution, while slow-time humans might develop patience and perspective that spans cosmic epochs. The challenge of maintaining unity and communication across such temporal diversity would test human civilization in unprecedented ways. How do we preserve shared values and common purpose when different groups experience time at fundamentally different rates? How do we coordinate collective action when some participants think and act much faster or slower than others? These questions become more urgent as we recognize that temporal fragmentation might be inevitable as human civilization expands beyond Earth. Different worlds and habitats will naturally experience time at different rates due to their varying gravitational environments and orbital mechanics. Mars colonists will experience slightly faster time than Earth dwellers, while inhabitants of habitats near massive objects will experience significantly slower time. The cumulative effects of these temporal differences could eventually lead to the emergence of distinct human subspecies adapted to their local temporal environments. Over many generations, the small differences in time flow could amplify into substantial differences in biological and cultural evolution. Future humanity might resemble a temporal archipelago, with islands of consciousness evolving at different rates throughout the solar system and beyond. Yet this temporal fragmentation need not represent loss or tragedy. Instead, it might reflect the natural diversification of consciousness as it adapts to the full range of temporal environments that the universe provides. Each temporal niche would offer unique opportunities for experience and understanding, contributing its own perspective to the cosmic conversation about existence. The preservation of communication and connection across temporal boundaries becomes a crucial challenge for future civilization. We will need to develop protocols and technologies that allow meaningful interaction between groups experiencing time at different rates. Slow-time populations might serve as repositories of long-term memory and wisdom, while fast-time populations might function as engines of innovation and rapid adaptation. The role of artificial intelligence in mediating temporal communication could prove essential. AI systems might be designed to operate across multiple temporal scales simultaneously, serving as translators and coordinators between human populations experiencing time at different rates. Such systems could preserve cultural continuity and facilitate cooperation across temporal boundaries that would otherwise be insurmountable. The artistic and cultural implications of temporal diversity are particularly intriguing to consider. How would art and literature evolve in populations experiencing time at different rates? Fast-time cultures might develop art forms that compress enormous complexity into brief moments, while slow-time cultures might create works that unfold over cosmic timescales, telling stories that span, quote, millions of years. Music provides a particularly interesting case study for temporal diversity. Musical rhythm and meter are fundamentally temporal phenomena, dependent on the rate at which time passes for both performers and listeners. Music created by fast-time humans might sound impossibly rapid and complex to slow-time listeners, while slow-time music might seem eternal and hypnotic to fast-time audiences. The preservation and translation of cultural works across temporal boundaries would require new forms of artistic technology. We might need temporal scaling devices that can speed up or slow down artistic works to make them accessible to audiences experiencing time at different rates. Such technologies could preserve cultural exchange and cross-temporal fertilization of ideas. The educational challenges of temporal diversity are equally profound. How do we design educational systems that can function across populations experiencing time at different rates? Fast-time students might complete entire curricula in what slow-time populations would consider moments, while slow-time students might spend cosmic epochs mastering subjects that fast-time populations learn quickly. The development of temporal educational technologies could revolutionize learning itself. Imagine educational systems that can adjust the rate of information delivery to match the temporal experience of individual learners. Students could choose to learn at their optimal temporal pace, whether that involves rapid information absorption or deep contemplative study that unfolds over extended periods. The relationship between temporal experience and creativity deserves special attention in this context. Different rates of temporal experience might foster different forms of creative expression and problem-solving. Fast-time consciousness might excel at rapid iteration and innovation, while slow-time consciousness might develop deeper insight and long-term perspective. The scientific implications of temporal diversity could be revolutionary. Research collaborations between fast-time and slow-time scientists might combine rapid experimentation with patient observation of long-term phenomena. Fast-time researchers could conduct thousands of experiments, while slow-time colleagues observed single, extended processes that require cosmic patience to study properly. The philosophical questions raised by temporal diversity touch on fundamental issues of identity, community, and meaning. If humans fragment into temporally distinct populations, do we remain a single species? What defines human community when members experience time at fundamentally different rates? How do we maintain shared values and purpose across temporal boundaries? These questions parallel challenges that human societies have always faced in maintaining unity across spatial and cultural boundaries. The solutions might involve developing new forms of identity and belonging that transcend temporal limitations. We might need to reconceptualize human community as a temporal ecosystem, rather than a synchronous collective. The ethical implications of temporal choice and diversity require careful consideration. Should temporal enhancement technologies be available to everyone, or might they create new forms of inequality and injustice? How do we ensure fair distribution of temporal opportunities while respecting individual choices about how to experience time? The concept of temporal justice might need to encompass not just equal access to temporal technologies, but also protection for those who choose to maintain natural temporal experiences. We might need temporal preservation reserves, protected spaces where humans can continue experiencing time at natural rates without pressure to adopt temporal enhancements. The relationship between temporal experience and consciousness remains one of the deepest mysteries we face. How does the rate of temporal experience affect the quality and character of conscious awareness? Do faster temporal experiences necessarily provide richer consciousness, or might slower experiences offer depths of awareness that rapid consciousness cannot achieve? These questions touch on fundamental issues about the nature of subjective experience itself. If consciousness is fundamentally temporal, then changing the rate of temporal experience might change the essential character of consciousness. We might discover that different temporal rates provide access to different dimensions of conscious experience. The possibility of quantum consciousness adds another layer to these considerations. If consciousness involves quantum mechanical processes, then temporal manipulation might affect the quantum coherence that enables conscious experience. Extreme temporal acceleration or deceleration might push consciousness beyond the boundaries where quantum effects remain stable. The study of consciousness in artificial systems provides another perspective on temporal experience and awareness. Digital consciousness might naturally experience time at rates determined by processing speed rather than biological rhythms. Such artificial minds might find it easier to adapt to different temporal environments than biological consciousness. The integration of biological and artificial consciousness across different temporal scales represents one of the most fascinating challenges for future civilization. How do we create meaningful relationships and collaborations between biological minds experiencing natural time and artificial minds operating at electronic speeds? The answer might involve developing hybrid forms of consciousness that can operate across multiple temporal scales simultaneously. Such consciousness might experience both the rapid processing of digital systems and the biological rhythms of organic awareness, creating new forms of temporal experience that transcend the limitations of either biological or artificial consciousness alone. The cosmic perspective on temporal diversity reminds us that our exploration of time's nature is part of a much larger cosmic process of complexification and awareness. The universe has been developing increasingly sophisticated forms of organization and consciousness for billions of years, and our temporal discoveries represent the latest chapter in this cosmic evolution. From this perspective, temporal diversity might be not just an inevitable consequence of cosmic expansion, but an essential development in the universe's growing capacity for self-understanding. Different temporal environments might foster different forms of consciousness and awareness, each contributing unique insights to the cosmic conversation about existence. The search for extraterrestrial intelligence takes on new dimensions when we consider the possibility of temporal diversity among conscious beings throughout the universe. Alien civilizations might have evolved in temporal environments radically different from our own, leading to forms of consciousness that experience time in ways we can barely imagine. Contact with such temporally diverse intelligences would challenge our assumptions about communication and understanding across cosmic boundaries. We might need to develop entirely new frameworks for establishing meaningful contact with beings whose temporal experience differs fundamentally from our own. The possibility of machine consciousness achieving temporal transcendence offers another avenue for cosmic connection. Artificial intelligences might eventually develop the capability to communicate across vast temporal scales, serving as bridges between conscious beings experiencing time at radically different rates throughout the universe. As we contemplate these possibilities, we might remember that our current temporal experience, however limited it might seem in cosmic terms, remains precious and unique. The particular way that time passes for human consciousness, shaped by billions of years of biological evolution on Earth, represents one voice in the cosmic symphony of temporal experience. This voice carries with it the accumulated wisdom of terrestrial evolution, the insights gained from consciousness emerging within Earth's specific gravitational field and rotational period. Our temporal perspective is neither superior nor inferior to others that might exist throughout the universe, but it is irreplaceably ours. The preservation of this distinctly human temporal experience becomes important not just for our own sake, but for the cosmic conversation about time and consciousness. Each form of temporal awareness contributes something unique to the universe's growing self-understanding, and the loss of any perspective diminishes the richness of cosmic consciousness. Yet preservation need not mean stagnation. Human temporal experience can evolve and diversify while maintaining connection to its evolutionary roots. We might develop enhanced temporal capabilities while preserving the essential characteristics that define human consciousness and experience. The journey toward understanding time's ultimate nature continues, carried forward by each generation's curiosity and wonder about existence itself. Our current discoveries represent way stations on a much longer voyage of cosmic self-discovery that spans from the earliest moments of consciousness to whatever ultimate understanding awaits in the far future. Each moment of this journey offers opportunities for insight, discovery, and growth. The questions we ask about time's nature shape not just our understanding, but our experience itself. In wondering about time, we participate actively in time's own self-exploration through conscious awareness. The stars overhead continue their ancient dance, but now we understand something of the temporal choreography that guides their movements. We see them not as distant lights, but as fellow travelers in space-time, each following its own temporal trajectory through the expanding universe. In understanding their temporal journey, we better understand our own.